Hello there, and welcome to The Tired Thinker, where curiosity slows down and big ideas gently unfold. Tonight's quiet exploration drifts into the strange world of probability paradoxes. These puzzles look simple, but the deeper you go, the more they bend logic and reveal how often our intuition gets things wrong. They'll tell you switching doors doubles your chances, that 23 people are enough for a shared birthday, and that fair doesn't always mean equal. Some feel impossible, some feel elegant. All of them reveal how uncertainty shapes everything, from choices and coincidences to how we understand reality itself. We rarely notice the hidden patterns guiding our lives. But probability is always there, silent, patient, powerful, perfect for late-night thinking or gently falling asleep. Before we begin, I'd love to know, where are you listening from? And what time is it right now in your corner of the world? It's funny, a video about uncertainty, yet here we are, quietly connected. If this soft thinking helps you unwind, I'd be grateful if you liked the video or gently subscribed. It helps this tired little channel find others who need a calm place to rest their minds. Now, let's begin. First pick had a 1/3 chance. The other two doors together had 2/3. When the host removes one losing door, the full 2/3 shifts to the remaining unopened door. It feels wrong, but works every time. Our senses like symmetry and balance. Probability does not care. Roll 2 dice. Many think every total from 2 to 12 has the same chance, but 7 is most common. There are 6 ways to make 7, but only one way to make 2 or 12. The math counts combinations. Our brains picture outcomes without weight. We also confuse chance with skill. In card games, players see streaks and think they are hot. Sometimes they are just lucky. Short runs of success happen in random sequences. True randomness often looks messy, but we expect random to look evenly spread. When randomness clusters, we think something is off. In sports, fans blame referees or talk about momentum, when randomness may explain the pattern. Probability demands context. If a medical test is 99% accurate, that sounds great. But what if the disease is rare? Say only 1 in 10,000 people have it. Even with a 99% accurate test, most positive results will be false positives. This is base rate neglect. We skip the overall rate and focus only on the test accuracy. Doctors train to avoid this error, but even experts slip. Let's build a scenario. You draw 1 card from a deck. What is the chance it is a king? Easy. 4 out of 52. But what is the chance of drawing at least 1 king in 2 draws without replacement? You could try adding probabilities, but it gets messy fast. The clean way is to find the chance of drawing no kings twice, then subtract from 1. Math gives clarity, but the process feels backward. This reveals how natural thought does not always match the rules. Probability also ties into risk. Driving a car feels safe. Flying feels dangerous. Yet flying is much safer. We judge risk based on emotion and memory. A plane crash is rare and dramatic. A car crash is common and forgettable. Probability strips away emotion. It looks at frequency and severity. Without it, our choices become reactive instead of rational. Insurance companies understand probability well. They price plans based on age, health, and history. They do not predict a single person's fate. They predict the group. This is the law of large numbers. Over many events, the average outcome becomes reliable. But as individuals, we focus on the one outcome that might affect us. Let's return to games. Consider poker. Good players do not think in terms of winning every hand. They think in expected value. If a move will win more over time, they make it, even if they lose sometimes. This mindset fights emotion. It accepts that short-term loss does not mean long-term failure. Probability teaches patience. A fun puzzle shows how framing changes perception. In a room, there are two children. At least one is a boy. What is the probability both are boys? Many say 1/2, but the correct answer is 1/3. The possible pairs are boy-boy, boy-girl, and girl-boy. Only one of these has two boys. Change the wording slightly, and people give different answers again. The structure of the problem matters more than the surface detail. Probability also deals with independence. If I roll a die twice, the outcomes do not interact. But if I draw 2 balls from a bag without replacement, the second draw depends on the first. People often mix these up. We assume independence where it does not exist, or assume dependence where it does not matter. Knowing the difference changes the numbers. Even experts fall into traps. During elections, people misread polls. A candidate with a 60% chance to win is not guaranteed to win. It means that in simulations, they win 6 out of 10 times. The underdog still wins 4 out of 10. Probability talks in ranges and likelihoods. We prefer certainties and single outcomes. Let's try another scenario. A friend has 2 coins. One is fair. One is biased and lands heads 90% of the time. They flip a coin 3 times and get heads each time. What is the chance they used the biased coin? Most people guess low numbers, but the biased coin makes 3 heads very likely. The fair coin makes that outcome rare. When we compare probabilities, the biased coin becomes the better explanation. This is Bayesian thinking. We update our beliefs based on evidence. Our brains resist this step because it feels like changing the answer midway. Probability forces us to respect uncertainty. It does not promise outcomes. It gives tools to navigate them. Some people find comfort in that. Others feel uneasy without guarantees. But understanding probability improves decisions. It helps in finance, sports, science, medicine, and everyday life. We can train intuition with practice. Work with real numbers, draw diagrams, simulate outcomes, roll dice, flip coins, watch patterns form. Over time, the math starts to feel less strange. We begin to trust it, even when it challenges instinct. The main struggle is letting go of the idea that the world should behave fairly or evenly in the short term. Probability reminds us that randomness has texture. It clumps, it surprises, it does not care about our feelings. Yet, beneath the noise, long-term patterns emerge. Math sees those patterns. Intuition often does not. Probability feels simple because the rules are clear, but intuition often leads us astray. The challenge is not the math. The challenge is our minds. Paradoxes feel abstract until we notice them in ordinary choices. They appear when logic collides with intuition or when simple rules stretch across countless outcomes. Infinity hides inside tasks we think are finite. We try to make sense of it, but the more we look, the stranger it becomes. Imagine you agree to walk halfway across a room then halfway again, then halfway again. Each step gets smaller. You never quite reach the other side. This is Zeno's paradox. In real life, you cross the rune in seconds. So which is true? Mathematically, infinite steps can add up to a full distance. But the idea of infinite actions packed into a few seconds clashes with how we think about motion. The paradox lives in how we frame the problem, not in the motion itself. Now picture choosing between two lines at the grocery store. You try to pick the shorter one. It still moves slower. You switch to another line. That one slows down too. It feels like you always end in the worst line. This is not just bad luck. In probability, most people will land in slower lines more often because there are many more ways for a line to be slow than fast. Infinite small variations shape our experience. What feels unfair is actually the most likely outcome. Paradoxes also surface in decision-making. Consider the unexpected exam scenario. A teacher tells the class there will be a surprise exam next week, but they won't know the day. The students reason that the exam cannot be on Friday because they would expect it on the last day. If it cannot be Friday, then it cannot be Thursday because Friday is ruled out. By reasoning backward, they remove every day. Yet the teacher still gives the exam on Wednesday, and everyone is surprised. The paradox comes from trying to use logic to eliminate all options while ignoring how surprise works in practice. Think about saving money. You plan to save more later, when things feel easier. You delay now because the future seems full of time and possibilities. But when the future arrives, it feels just like the present. This repeating pattern is a temporal paradox. You always stand in a moment that feels urgent, so you never act. Each moment seems small, but stretched across time, it becomes infinite delay. The contradiction comes from treating future you as different from present you. Infinity often hides in choices with looping outcomes. In the paradox of intolerance, a tolerant society must decide whether to tolerate intolerant behavior. If it tolerates intolerance, intolerance may destroy tolerance itself. If it refuses to tolerate intolerance, what becomes intolerant? The system circles around itself. Each decision carries consequences that feed back into the starting condition. Rules that work on small scales collapse on large ones. Let's look at a hotel with infinite rooms. This is Hilbert's Hotel. Every room is full. A new guest arrives. The manager moves the guest in room 1 to room 2, room 2 to room 3, and so on. Now room 1 is open. The hotel was full, yet it fits more people. Math says infinity has room. Intuition says full means full. The paradox reveals that infinite sets break everyday logic. Choices with uncertain impact can feel paradoxical too. Voter's paradox. Voting seems pointless because a single vote rarely changes an outcome. But if everyone thinks this way, no one votes and the system fails. If everyone does vote, each person's choice supports the system. The result depends on collective behavior, not individual power. Infinity appears in the huge number of possible voting combinations. The paradox sits in the tension between personal logic and group effects. We also see paradox in trust. You promise to keep a secret, but you know the person who told you would want someone else to know if it helped them. Telling might honor their true interest, but break their explicit request. Both loyalty and honesty point in different directions. A single choice holds two conflicting truths. The closer you look, the more paths appear. Consider a simple game. You flip a coin until you get tails. Each flip, the prize doubles. $1, $2, $4, $8, and so on. The expected value of the game is infinite. But how much would you pay to play? Most people offer a small amount. The math says the game is worth infinity. Real intuition says the game is not worth much because large payouts are rare. This is the St. Petersburg paradox. It exposes the gap between infinite expectation and human judgment. We value utility, not raw expectation. Infinity lurks in the numbers, but our choices stay grounded. Even free will has paradoxes. If every choice comes from prior causes, are we free? If choices are random, are we still responsible? We feel like we choose, yet our choices rest on infinite threads of memory, habit, and influence. Trying to isolate a single decision is like trying to catch water with your hand. The closer you look, the more it slips. Paradoxes also emerge in fairness. You split a bill equally. One person ordered less and feels cheated. You adjust based on what each person ate. Now someone complains about tax or tip. You adjust again. Each change solves one issue, but reveals another. The more precise you try to be, the more disputes appear. Fairness becomes an infinite negotiation. A simple goal unravels into endless adjustments. Let's explore time travel. You go back in time and prevent your grandparents from meeting. Then you would never be born to go back in time. This causal loop is the grandfather paradox. It breaks logic because cause and effect flip. Physicists explore ways around it, like alternate timelines, but everyday cause and effect fail when time loops. We try to apply linear rules to infinite branching paths. Even identity holds paradox. The ship of Theseus asks, if you replace every part of a ship over time, is it still the same ship? If you rebuild the original parts into a new ship, which one is real? Both answers feel right and wrong. The paradox reveals that our idea of identity depends on context, not fixed logic. Everyday objects hide infinite states over time. Small choices also lead toward paradox when they compound. You bend a rule once, it feels harmless. You bend it again. Over time, the rule disappears. Each action seems minor, but together they create a different world. Morality can break under gradual change, not sudden collapse. Infinity sneaks in through repetition. The liar paradox takes a simple sentence. This statement is false. If it is true, then it is false. If it is false, then it is true. The sentence traps itself. Language allows self-reference, and self-reference opens the door to infinite loops. We treat statements as stable, but some statements point back at themselves, forming logical knots. Everyday life is full of these knots. We promise to be spontaneous. We plan to relax. We force creativity. Each goal cancels itself. Trying to be effortless creates effort. Trying to let go tightens our grip. The paradox emerges not from failure, but from the structure of the goal. It contains two directions at once. Paradoxes do not always mean something is wrong. They often show the limits of how we frame choices. When a simple idea meets infinite possibilities, our rules bend. We try to compress infinity into a straight line, and the line twists. Paradoxes remind us that logic has edges, and beyond them, everyday life is more complex than it seems. Our brains crave order. We want answers we can rely on, patterns we can trust, and rules that do not shift. We like when cause leads to effect in a straight line. Probability challenges that comfort. It does not say yes or no. It says maybe. It does not promise results. It offers chances. It forces us to live with uncertainty, and that makes many people uneasy. Imagine someone rolling a die. You ask, what number will come up? They shrug. That shrug is probability in action. We know each side has a 1 in 6 chance, but we cannot know the result ahead of time. Our minds prefer concrete answers, so we try to predict anyway. We search for clues. We convince ourselves we see patterns. We feel more confident than the math allows. When things happen, we often rewrite the story so it makes sense. If a team wins 3 games in a row, people say they are on fire. If they lose, people say they fell apart. These explanations sound certain, but often luck plays a bigger role than we admit. Probability does not fit clean stories, so we replace it with narratives that feel solid. Look at coin flips. If you flip a coin and get 5 heads in a row, most people think tails must be next. This is the gambler's fallacy. Each flip is independent. The coin has no memory. Yet our brains hate imbalance, so we imagine fairness must happen in the short term. Probability operates over long sequences. Our intuition focuses on the moment. The two clash. Even when we understand the math, uncertainty still bites. Say a medical test is 99% accurate. That sounds certain. If you test positive, you panic. But if the condition is extremely rare, the chance you actually have it may still be low. This is base rate neglect. We latch onto the 99% and ignore the bigger picture. Probability requires context. Certainty ignores it. Picture choosing a line at the grocery store. You pick one that looks fast. It slows down. You switch. The new line slows too. It feels personal. In reality, there are many more ways for a line to be slow than fast. Probability says you'll often wait longer than you expect. Your brain says the world is unfair. Both feel true. Only one reflects the math. We struggle with risk because uncertainty makes us uncomfortable. Flying feels dangerous because plane crashes are vivid. Driving feels safe because accidents are common and forgettable. But flying is far safer. Our fear does not come from probability. It comes from emotion. We confuse possibility with likelihood. Probability separates the two. In daily life, we act like outcomes are certain. We plan careers, we invest money, we trust relationships. We think effort guarantees success, but effort only increases odds. It never guarantees. Someone might work hard and still fail. Someone else might succeed with less effort. Probability sits in every path we take. We just prefer to ignore it. Consider the Monty Hall problem. 3 doors, 1 prize. You choose a door. The host opens a different door to reveal nothing behind it. Should you switch? Most people stay, thinking the odds are even. But switching doubles your chances. It feels wrong, yet the numbers are clear. Intuition wants balance. Probability follows structure. When they disagree, intuition usually wins in our minds, even when it is wrong. We like stories with heroes and causes. If someone becomes rich, we point to smart decisions. If someone fails, we blame poor choices. We overlook how much randomness affects life. The right moment, the right environment, the right chance meeting. All of these shape outcomes. Probability explains it. Certainty dismisses it. In games like poker, good players do not focus on single hands. They think in long-term expected value. A decision may lose now, but win across many rounds. This mindset is hard because our brains judge each result as success or failure. Probability asks us to zoom out. Certainty keeps us zoomed in. In business, leaders make predictions with confidence. They say a product will succeed or fail. The truth is, they are estimating probabilities, even if they do not say it. Markets shift. People behave unpredictably. Surprises happen. The world resists certainty. The best decisions manage risk, not eliminate it. Probability shows up in moral choices too. Imagine driving at night on a quiet road. You see a stop sign. You could roll through it. The chance of an accident is low, but low is not zero. You stop anyway. You weigh the risk. You accept uncertainty. Probability guides your behavior even when you think you are acting on principle. Some people try to beat uncertainty by gathering more information. They research every option, compare every minor detail, and delay action until they feel confident. Yet total certainty never arrives. At some point, probability demands a leap. The fear of being wrong often leads to no action at all. That avoidance is driven by a need for certainty that probability refuses to give. Randomness can even look like intention. If you flip a coin 100 times, you might see a streak of 10 heads in a row. It feels suspicious. But in a long sequence, streaks are expected. Probability allows clusters and patterns. Our brains label them meaningful. We invent reasons instead of accepting chance. This is why people see luck, fate, or manipulation where none exists. We also misunderstand rare events. If something has a 1 in a million chance, we treat it as impossible. But in a world of billions of people and constant activity, 1,000,000-to-1 events happen every day. Probability does not just live in math problems. It lives in reality. Rare does not mean never. Likely does not mean guaranteed. Let's say you meet someone, fall in love, and think it was meant to be. But think of how many small events led to that moment. Where you were, who you knew, timing, mood. 1,000 tiny probabilities lined up. It feels like destiny. It was probability at work. Probability is not cold or detached. It describes how the world behaves. It protects us from false certainty. It tells us that knowledge has limits. It teaches humility. Yet we still crave guarantees. We want a universe to tell us yes or no, not maybe. Our brains evolved to survive, not calculate. In the wild, hesitation could kill. Fast, confident decisions helped us stay alive. But in modern life, many problems are probabilistic. Investments, health, technology, relationships, weather, politics, all driven by uncertainty. Certainty feels comfortable, but it can blind us. Embracing probability does not remove doubt. It makes us honest about it. To live with probability is to accept that control is partial, that success is not pure merit, that failure is not pure fault, that the future cannot be locked in. Our brains resist this. But once we learn to think in probabilities, our choices become clearer. We prepare for many outcomes instead of relying on one. We see patterns without forcing them. We respect randomness without fearing it. Certainty is a promise the world rarely keeps. Probability does not promise. It whispers maybe, and in that quiet honesty, it tells the truth. A small shift in how we look at something can flip our entire understanding of it. Perspective works like a lens. It does not change reality, but it changes what we notice, how we react, and the choices we make. What seems obvious from one angle becomes confusing from another. What feels impossible one moment becomes manageable when seen differently. The surface stays the same, but the meaning changes. Imagine a glass with water. Some people see it as half full, others as half empty. This example gets overused, but the reason it sticks is simple. The amount of water does not change, only the mindset does. One view focuses on what is there, the other on what is missing. That small mental frame changes mood, decisions, and expectations. Perspective also shapes conflict. Two people can look at the same event and tell different stories. One might feel attacked, while the other believes they were being honest. Neither is lying. They are standing in different mental positions. If each person shifted slightly, trying to see what the other sees, the tension might dissolve. But we cling to our angle because it feels like the truth. We forget that someone else might be standing in a different spot, looking at the same thing. Consider time. When we make a mistake, we judge ourselves harshly. But when a friend makes the same mistake, we feel understanding. The action is identical. Only the viewpoint shifts, from inside the moment to outside it. Distance creates compassion. Stepping back gives us calm. Sometimes perspective is not about changing facts, but about changing closeness. Small changes in perspective reshape risk. Think about investing. Many people panic when a stock drops. They see loss and pull out. Long-term investors see dips as discounts. The market is the same. One sees danger, the other sees opportunity. Fear or patience depends on time horizon. A shift in time perspective transforms the same data into a different decision. The famous Monty Hall problem shows how perspective alters probability. 3 doors, 1 prize. You pick a door. The host opens an empty one. Should you switch? If you look only at the 2 remaining doors, it seems 50-50. But if you step back and consider the whole setup, switching doubles your odds. Seeing the structure instead of the moment changes the answer. The puzzle becomes clear only when you adjust the frame. Perspective also affects value. Say you find $20 on the street. You feel lucky. Then you find out your friend just got a $1,000 bonus. Suddenly, your $20 feels small. The amount did not shrink, only the comparison changed. Our minds measure through contrast. Perspective defines whether we feel rich or lacking. In relationships, a tiny shift can open or close connection. If someone snaps at you, you might feel insulted and snap back. But if you pause and imagine they might be tired or stressed, your response softens. Nothing external changes. You still hear the same words, but perspective changes the emotional outcome. You choose to interpret instead of react. Even goals depend on viewpoint. Someone says, "I have to go to work." It sounds heavy. Someone else says, "I get to go to work." Same situation. One sees burden, the other sees agency. This small language shift changes energy and motivation. It is not fake positivity. It is choosing a frame that highlights control. Perspective reveals hidden layers in everyday choices. Take the idea of fairness. If 3 people split a bill evenly, one person might feel cheated because they ate less. Another sees equal pay as simplest. A third sees group harmony as more important than accuracy. Each person uses a different lens to define fairness. One situation, many truths. In sports, a team might lose by 1 point. From one view, they failed. From another, they competed well. From another, they learned something important. The score stays the same. The story changes. Athletes who recover from losses do so by shifting perspective. They do not ignore failure. They reinterpret it. Memory itself changes with perspective. When something painful happens, it feels overwhelming. Later, looking back, the same event might look like growth. The past does not move, but our position in relation to it does. Perspective turns scars into lessons. Choosing the right frame can fix paradoxes. Take the classic trolley problem. A trolley is heading toward 5 people. You can pull a lever to redirect it onto a track where it will hit one person. Do you act? Many people struggle because they see the situation in black and white. But shift the frame from killing versus letting die to minimizing harm, and some people find clarity. The facts do not change. The ethical lens does. Consider trust. If someone disappoints you, you can see it as betrayal or as a sign they are human. One view closes you off. The other keeps connection possible. Perspective allows forgiveness without ignoring reality. It also protects you from taking everything personally. Learning works the same way. Some people avoid hard tasks because they fear failure. They see ability as fixed. Others view challenges as tools to grow. The task stays the same. The mindset changes the outcome. This is the difference between a fixed mindset and a growth mindset. A shift in belief transforms effort. Even perception of time can change results. When you say, "I do not have time," you focus on limits. When you say, "This is not a priority," you focus on choice. The second feels more honest, and it forces clarity. Perspective replaces helplessness with responsibility. Perspective also changes how we deal with randomness. When something good happens, we claim credit. When something bad happens, we blame luck. But sometimes success also involves luck, and sometimes failure involves effort. Seeing both sides gives balance. It replaces ego with understanding. It helps us treat others with more empathy and ourselves with more fairness. Small shifts in viewpoint can even turn conflict into cooperation. Imagine two coworkers arguing about how to solve a problem. Each defends their solution. If they reframe the situation as us versus the problem, instead of me versus you, everything changes. They stop protecting ideas and start building together. The problem stays, but teamwork emerges. Sometimes perspective is physical. A painting looks flat up close. Step back and the image appears. Life is similar. Up close, we get lost in details. From a distance, patterns emerge. Perspective adds depth. It reveals connections we could not see before. We often assume perspective shifts require major effort, but often it takes only one question. What if I am looking at this the wrong way? What else could this mean? What would this look like from the outside? These questions pull us out of rigid thinking. They give space for insight. The world does not always change. We change how we look at it. And that change can turn confusion into clarity, conflict into understanding, and obstacles into possibilities. A small angle difference can send a path in a whole new direction. Perspective is power, not because it alters facts, but because it transforms what facts can become. Paradoxes sneak into our thinking when we try to force tidy logic onto a world filled with randomness. They show up when our rules collide with uncertainty. We expect clean answers, but probability bends the path. Logic feels solid until chance gets involved, and then even simple problems twist into confusion. Paradoxes are not mistakes in math. They are clues that our intuition struggles when randomness plays a role. Take the Monty Hall problem. 3 doors, 1 prize. You pick a door. The host opens another door showing no prize. Most people think the odds are now 50-50 between the remaining 2 doors. It feels fair. But switching doors gives you a 2/3 chance of winning. Staying gives you only 1/3. The math is clear. The logic feels wrong. Randomness hides structure, and that structure fools us. The paradox comes from trusting gut instinct over probability. The birthday paradox is another classic. In a room of 23 people, the odds that 2 share a birthday are about 50%. That seems impossible. There are 365 days. 23 is tiny compared to that. But the comparison is not one person to the group. It is every pair in the group. There are many possible pairs, and each pair has a chance to match. Randomness stacks possibilities quietly. Our intuition ignores the number of combinations. The result shocks us because we think too narrowly. Look at the gambler's fallacy. Flip a coin 5 times and get heads each time. Most people think tails is now more likely. It feels overdue, but the coin has no memory. Each flip is still 50-50. Logic tells us randomness should balance out immediately, but probability works over long sequences. The paradox appears because we expect fairness in the short term. Chaos does not care about symmetry. Randomness also makes decisions tricky. In the paradox of choice, more options should be better. Logic says more freedom equals better outcomes, but too much choice often leads to indecision, regret, and anxiety. We fear picking the wrong option because the alternative outcomes feel infinite. Randomness in outcomes turns logic inward. We start doubting our own judgment. The paradox lies in the gap between theoretical freedom and emotional burden. Randomness creates scenarios where small changes erase certainty. Consider the liar paradox. This statement is false. If it's true, it's false. If it's false, it's true. The loop breaks logic. Probability can do the same. Imagine a scenario where acting changes the odds of success in ways that depend on your own prediction of the outcome. Self-reference blends with randomness and logic collapses. When an action influences the situation you are trying to measure, you end up chasing your own tail. Game theory exposes similar paradoxes. In The Prisoner's Dilemma, 2 people face a choice: cooperate or betray. Logic says betrayal is safer, but if both betray, both lose. Cooperation gives the best combined result, but individual logic destroys it. Randomness in the other person's choice makes clear strategy impossible. The paradox is that rational thinking leads to worse outcomes than trust. Randomness breaks pure logic because logic depends on prediction. Probability also flips our expectations in everyday life. Think about regression to the mean. If someone has an amazing performance, the next one will likely be closer to average. People think this is a decline. In reality, it is randomness settling. But we build stories to explain the change. Pressure, nerves, lack of effort. We want cause and effect. We resist chance as an explanation. The paradox comes from mistaking noise for signal. Even simple questions can turn strange when probability enters. Imagine 2 children in a family. You're told that at least one is a boy. What are the odds both are boys? Many people say 1/2, but the correct answer is 1/3. The possible combinations are boy-boy, boy-girl, and girl-boy. Only one of these has 2 boys. The confusion happens because randomness interacts with wording. The logic feels straightforward, but probability lives in the structure of the information, not the surface of the statement. In the St. Petersburg paradox, a game offers a coin flip with a prize that doubles each time you get heads. The expected value of the game is infinite, but people will not pay more than a small amount to play. The math says the game is infinitely valuable. Reality says it is not. The paradox exposes a flaw in how expected value works with infinite outcomes. Randomness stretches logic to the breaking point. Risk creates paradoxes in human behavior. Voting is a clear example. One vote almost never changes an election. Logic says not voting is rational. But if everyone follows that logic, democracy collapses. Collective outcomes often depend on individual actions that seem pointless. Randomness across the population makes the system work, but logical thinking at the individual level undermines it. The paradox lies between personal logic and group stability. Time introduces its own layer of randomness. In the waiting paradox, the average wait time for a bus is longer than half the interval between buses. This happens because you are more likely to arrive during longer gaps. Random arrival meets uneven spacing, and the result feels unfair. People think the system is broken, but it is just probability at work. Logic expects symmetry. Randomness builds bias. Even trust gets tangled in paradox. Think about the saying, trust but verify. If you trust fully, you do not verify. If you verify, you signal distrust. Both actions contradict each other, yet both feel necessary. Add randomness, uncertainty about intentions, and logic slips. The paradox lives in the tension between safety and connection. Randomness shows us that clear logic sometimes hides assumptions. Take sports streaks. A player makes 5 shots in a row. People say he is hot, but data shows streaks often match what pure chance would produce. Our brains search for patterns, even in noise. When chance delivers a pattern, we treat it as skill or momentum. Logic gets replaced by storytelling. The paradox is that randomness often looks more ordered than actual design. Human memory adds to the confusion. The peak-end rule says we judge experiences based on the most intense moment and the ending, not the average. 2 events with the same total pain can feel different depending on how they finish. Random spikes of emotion shape logic. We believe we are rational, but memory bends truth. The paradox: our decisions about future events are based on distorted versions of past ones. Some paradoxes warn us that logic without randomness is incomplete. If you avoid small risks completely, you often create bigger risks later. Trying to eliminate uncertainty leads to fragility. Systems that allow randomness, small shocks, small losses, become stronger. This is anti-fragility. It runs against logic that says safety is always better. The paradox is that embracing randomness can create stability. Logic wants clean rules. Randomness creates messy realities. When the two meet, they do not blend, they clash. Paradoxes are the cracks that form when certainty tries to cover uncertainty. They remind us that logic is a tool, not a map of the world. They show that randomness is not the enemy of reason, but the test of whether our reason is flexible enough to handle real life. Sometimes math looks confusing, not because the numbers are hard, but because the question is shaped in a way that misleads us. A tiny shift in wording can flip the meaning. Our brains latch onto the surface and miss the structure. When results seem strange or impossible, we often blame the math. But in many cases, the real issue is that the question guides us down the wrong path from the start. Take probability problems. The classic example is the Monty Hall scenario. 3 doors, 1 prize. You pick a door. The host opens another door with no prize. Should you switch? Many people think the odds are now equal, so switching does not matter. But that view comes from framing the situation as a fresh 50-50 choice. The better frame is to see your first pick had a 1 in 3 chance, and the remaining 2 doors held 2 in 3. When the host removes a losing door, the whole 2 in 3 shifts into the last door. The answer only feels wrong if we frame it as 1 door versus 1 door. When we frame it as initial chance versus redistributed chance, the problem clears up. The birthday paradox is another case. Someone asks, what are the odds 2 people share a birthday in a room of 23? Most people compare 23 to 365 and assume the odds are low. But the right frame is not 23 people versus 365 days. It is how many pairs exist among 23 people. There are 253 possible pairs, and each pair has a chance to match. Once you see the problem as pairs instead of individuals, the high probability makes sense. Framing affects emotion too. If a doctor says a treatment has a 90% survival rate, patients feel confident. If the doctor says it has a 10% death rate, patients feel uneasy. The numbers are the same, only the framing changes. The math never moved, the meaning did. Even simple arithmetic can look wrong when framed poorly. Imagine you drive halfway to a location at 60 miles per hour and return halfway at 30 miles per hour. People often average the speeds and say 45 miles per hour. But that frame assumes equal time, not equal distance. The correct frame is total distance over total time. Once you reframe, you see the trip takes 1 hour total, so the average speed is 40 miles per hour. The error comes from framing the wrong quantity as equal. Framing also bends fairness. Suppose you split a restaurant bill evenly among friends. It seems fair if everyone ate similar meals. But if one person only had a drink, they feel cheated. The question, what is fair, changes based on whether you frame fairness as simplicity, accuracy, or harmony. Each frame produces a different answer. None are mathematically wrong. They just solve different versions of fairness. Many paradoxes vanish when the question is reframed. The unexpected exam puzzle tells students they will get a surprise test next week. They reason backward and prove it cannot happen. Yet when the teacher gives the test, everyone is surprised. The flaw is in the frame. The students assume perfect prediction. The paradox exists because the question blends logic about certainty with human behavior. If you reframe it as a surprise is relative, not absolute, it stops being a paradox. Framing also shapes how we judge risk. If a study says a drug doubles the risk of a rare side effect, people panic. But if the absolute risk goes from 1 in a million to 2 in a million, the actual danger remains tiny. The first frame exaggerates. The second clarifies. Math stays constant. Framing drives fear. Even in everyday decisions, framing can trap us. You decide whether to take a new job. You ask, is this better than what I have? That frame compares comfort to change. But a better question might be, which future gives me growth? Now the perspective shifts. Instead of holding on, you look forward. The job did not change. Your frame of value did. In relationships, framing determines reactions. Someone cancels plans. You can frame it as disrespect, or you can frame it as exhaustion. The same event can trigger anger or empathy. You are not changing the facts, only the meaning you attach. Framing builds stories, and stories shape feelings. Framing impacts strategy too. In game theory, the prisoner's dilemma looks like a simple choice: cooperate or betray. It feels like an argument about trust. But if you reframe it as what outcome is best for both players, cooperation becomes logical. The original framing isolates individuals. The better framing connects them. Even logic puzzles become clearer with the right frame. Ask someone. A bat and ball cost $1.10. The bat costs $1 more than the ball. How much is the ball? Most people say 10 cents. They frame it as a quick subtraction problem. But the better frame is a simple equation. Ball equals X. Bat equals X plus 1. Total equals 2X plus 1 equals 110. Now 2X equals 0.10, so X equals 5 cents. The math is easy once the frame is accurate. The tricky part was choosing the wrong frame for mental shortcuts. Framing also helps solve emotional paradoxes. Someone says, I'm stuck. Underneath, the frame is, I need the perfect answer before I act. If you reframe to, I will learn by acting, progress becomes possible. The problem was not the situation. It was the rule hiding in the question. We often ask narrow questions that force narrow answers. How do I avoid failure? Leads to hesitation. How do I move forward despite risk? Leads to action. The frame behind the question reveals what we really care about. Sometimes the smartest move is to throw out the question and ask a better one. Even identity can be reframed. The ship of Theseus asks whether a ship remains the same after all its parts are replaced. The paradox depends on framing identity as physical continuity. If you reframe identity as function or history, the paradox changes shape. The problem is not answered by logic alone. It depends on how you define same. Math stays consistent. Frames shift meaning. Ask the wrong version of a question, and the right answer looks wrong. Ask the right version, and complex ideas become simple. Reframing does not change reality. It changes the path to understanding. Many of our toughest problems dissolve when we stop wrestling the math and start reshaping the question. Probability forces us to see the world as it is, not as we think it should be. It challenges our sense of fairness and exposes how our instincts mislead us. We like to believe the universe balances itself. We expect effort to bring reward, risk to bring danger, and chances to spread evenly. But randomness does not follow our beliefs. It behaves in ways that often feel unfair, even when the math is sound. Probability teaches humility by reminding us that intuition is not always truth. Imagine flipping a coin 10 times and getting 7 heads. It feels wrong. A fair coin should give 5 heads and 5 tails, or something close. But fairness in probability does not mean every short sequence will be balanced. Fairness means that over a very large number of flips, the average will settle around half. In the short term, randomness is lumpy. What feels unfair is often perfectly normal. Our mistake is expecting the world to behave fairly in every moment, not over time. Consider how we judge luck. Someone wins the lottery twice. We assume cheating. It must be impossible. But in a world with millions of players and many different lotteries, rare events happen often. Probability does not care about what should happen. It cares about how many chances exist. With enough trials, extreme outcomes become expected. Fairness does not mean average outcomes every time. Fairness means every outcome follows the rules, even the strange ones. This shows up in everyday life. You stand in line at the grocery store, pick the shortest one, and watch it slow to a crawl. You switch to another line. It slows down too. You feel cursed. But on average, most people end up in slower lines more often than fast ones. Why? There are more ways for a line to slow down than to speed up. Reality is not symmetrical. True fairness allows imbalance because chance is uneven in its patterns. We think fairness means equal experience. Probability says fairness means equal rules, not equal outcomes. Consider sports. A player makes 5 shots in a row. People say they are hot. Another player misses 5 and is called cold. But long streaks happen even in completely random sequences. We see patterns and assign meaning. We want to believe skill or momentum explains everything. Probability tells us streaks occur by chance more often than we expect. Our sense of fairness makes us believe success must come from effort and failure from flaws. Probability shows that luck plays a larger role than we like to admit. This is where humility comes in. Probability forces us to accept that control is limited. You can make perfect choices and still lose. You can make bad choices and still win. Fairness does not guarantee the outcome you want. It just sets the stage. Many people struggle with this idea because it removes certainty. But accepting uncertainty helps us make better decisions. Instead of judging results, probability asks us to judge process. Think about poker. A skilled player might lose a hand to a beginner. That does not mean the beginner is better. It means luck favored them in that moment. A fair game still allows unfair-looking results. Over many hands, the skilled player wins more often. But that long view requires patience. Probability rewards consistency, not comfort. It humbles us by showing that one moment proves nothing. We also misunderstand risk because we confuse possibility with likelihood. Flying feels dangerous because plane crashes are dramatic. Driving feels safe because accidents are common and quiet. The truth is the opposite. Probability strips away emotion and reveals reality. Fairness is not what feels safe. It is what the data supports. Our instincts want stories, not statistics. Probability refuses to tell comforting stories. Even moral judgment can be distorted by randomness. If someone succeeds, we credit hard work. If someone fails, we blame poor choices. But probability reminds us that environment, timing, and chance shape outcomes more than we admit. Two people can make the same effort and land in very different places. Fairness in life is not guaranteed. Humility means recognizing that luck is part of every story, including our own. Consider this scenario. Two job candidates have equal qualifications. One gets the job because their interview happened on a day the hiring manager was in a good mood. The other meets the manager after a stressful meeting. Is that fair? We like to believe merit decides everything, but randomness seeps in through timing, mood, and context. Probability exposes the hidden variables we overlook. A Monty Hall problem shows how fairness and logic can clash. At first glance, sticking with your first door seems fair. Switching seems like cheating the system. But the math says switching is the better move. Fairness here means using all available information, not sticking with instinct. Our sense of fairness often ignores new evidence because we anchor on initial choices. Probability humbles us by revealing how stubborn our thinking can be. The birthday paradox feels unfair too. How can 23 people produce a 50% chance of shared birthdays? We expect each person to compare with the whole group, but the real question is how many pairs exist. Probability looks at structure. Intuition looks at surface. The result feels wrong because we framed fairness in the wrong way. Even time contains hidden unfairness. If buses come every 10 minutes, the average wait time should be 5 minutes. But in reality, the average wait is often longer. Why? You are more likely to arrive during a long gap than a short one. Chance tilts experience. Fairness is technical, not emotional. Math shows us truth, even when we do not like it. Regression to the mean also complicates fairness. A person performs incredibly well one day. The next day, they do worse. They feel like they slipped. Others think they slacked off, but the truth is that extreme results move back toward average simply because of randomness. Fairness in data does not mean steady performance. It means letting variation breathe. Punishing normal variance is unfair. Probability helps us see that. We also face the problem of sample size. A small set of events can look wildly uneven. A coin might land heads 8 times in a row. It looks rigged. But if you flip it thousands of times, the pattern evens out. Fairness emerges over scale. Our lives are lived in small samples. We judge fairness too early. Probability teaches resilience. It tells us not to overreact to one success or one failure. It encourages us to look at trends, not moments. It makes us skeptical of easy judgments. It reminds us that luck is not cheating. It is part of the system. When we accept that, we stop blaming the world for every loss and stop taking full credit for every win. The world is not built to match our sense of fairness. It is built on chance, structure, and complexity. Probability does not remove fairness. It redefines it. It teaches humility by showing us that fairness is not always visible, not always instant, and not always equal. Accepting this truth does not make us passive. It makes us wiser. It helps us act with clarity rather than illusion. Probability does not comfort us. It wakes us up. The more we try to understand reality, the more unpredictable it becomes. On the surface, life looks structured. We wake up, follow routines, and see patterns. But once we start asking deeper questions about behavior, nature, choices, or even our own minds, we find uncertainty hiding underneath. The world stops behaving like a machine and starts behaving like a guessing game. Think about people. We want to believe we know why others act the way they do. We create reasons. They said this because of that. They chose this because of logic. But motivation is layered. Someone can be kind for selfish reasons or rude out of fear. Two people in the same situation may react in opposite ways. The deeper you look, the more variables appear. Personality, memory, mood, past experiences, social pressure. You try to build a clean explanation, then one more detail flips it. Predicting people becomes guesswork disguised as certainty. Probability reminds us that even when patterns exist, they do not guarantee outcomes. A person can make smart choices and still fail. A reckless person can get lucky. Luck is not a myth, it is a force. In markets, weather, sports, and relationships, randomness plays a bigger role than we admit. We look back and invent stories that make events seem obvious. We forget that before things happened, they could have gone in many directions. Reality is full of branching paths, most of which we never see. Science deepens the mystery. In physics, classical systems follow clear rules. Drop a ball, it falls. Push something, it moves. But go down to the quantum level, and certainty vanishes. Particles do not sit in one place until measured. They exist in probability clouds. They can be in many states at once. Only when we observe do they choose. Even experts struggle to explain what that means. The more precise our tools, the blurrier the world looks. Nature itself seems to operate on maybes. Even logic bends when uncertainty enters. Game theory tries to predict strategic decisions. It builds models where each player thinks about what others might do. But then each player thinks about what the others think they might do. This infinite loop makes outcomes unstable. You can never fully know the other side's mind. Strategy becomes layered guessing. What looks rational in isolation becomes unpredictable in interaction. Consider risk. We use probability to measure it, but risk never sits still. You might think driving the same route every day is safe, but someone else's decision can change everything. You cannot control all variables. Systems with many moving parts, economies, ecosystems, cities, behave in non-linear ways. A small change can cause massive effects. The deeper we analyze them, the more fragile our predictions become. Even memory, the thing we rely on to make sense of reality, is unreliable. We think we recall events accurately, but memory edits itself. Our brains rewrite the past to match our beliefs. two people can remember the same moment in opposite ways. Which version is real? We assume reality is objective, but we live inside perception. The deeper we explore the mind, the harder it becomes to draw a line between truth and interpretation. In everyday life, decisions feel straightforward on the surface, but look closer and complexity explodes. Should I take this job or that one? It seems like a simple A or B, but each choice branches into countless outcomes depending on timing, relationships, health, timing, and chance. A single meeting can change everything. A delay can unlock new paths. It is not that choices do not matter. It is that we can never know what each choice truly contains. We make decisions based on limited information, then justify them later as if we knew all along. Probability teaches that uncertainty is not a flaw in thinking. It is built into reality. No model sees everything. No forecast reaches perfect accuracy. Even perfect information would not give perfect prediction if randomness plays a role. We want guarantees, but the world only offers ranges, likelihoods, and tendencies. That can feel uncomfortable, but it can also be freeing. If certainty is impossible, then we do not have to waste energy pretending it exists. Think about weather. Meteorologists have powerful tools and huge data sets. They can predict broad patterns well, but the exact path of a storm remains uncertain even hours before it hits. Chaos theory explains why. Tiny changes in starting conditions produce massive changes later. We cannot measure every variable, so exact prediction is out of reach. Weather is not random. It follows rules, but those rules interact in ways that make the final result feel like a guess. The same principle appears in social systems. Trends, movements, and markets follow patterns, but small actions can trigger big shifts. A single tweet can move stocks. A small protest can spark global change. No one sees it coming until it happens. Only afterward do we build clean narratives that make it look obvious. We rewrite randomness into logic to stay comfortable. But if you stare long enough, you see the threads of chance woven everywhere. Even language reveals the guessing nature of reality. Words shift meaning over time. Context changes interpretation. A phrase that sounds harmless to one person can hit another like an insult. Communication is not a clean transfer of information. It is an act of translation shaped by mood, tone, and assumptions. We think we say one thing. Others hear another. Understanding is a probability, not a certainty. Morality becomes complicated as well. On the surface, right and wrong look clear, but deeper in, intent, context, and consequences collide. A choice may help one person and hurt another. What seems fair in one frame becomes unfair in another. The more perspectives you consider, the less absolute morality becomes. Values remain important, but applying them becomes a messy, uncertain process. We guess, we adjust, we learn. Even self-knowledge becomes a guessing game the deeper we look. We say we know who we are, but our preferences change. Our goals evolve. We react differently in new environments. We think we are consistent, yet half of our behavior is influenced by context we do not notice. We discover things about ourselves by accident. What we believe is stable identity might be a moving pattern. The deeper we search for the core of self, the more it slips away. None of this means reality is chaos. Patterns still exist. Rules still apply. But the deeper we examine them, the more we see exceptions, edge cases, and hidden variables. The world is not a perfect puzzle to solve. It is a dynamic web of probabilities. Certainty belongs to simple views. Depth reveals complexity, and complexity demands humility. The irony is that we crave understanding, so we keep digging. But the more we dig, the more we uncover unpredictable layers. In science, philosophy, psychology, and life, we find that every answer opens up more questions. Reality does not hand us final truths. It offers glimpses. In the end, the deeper we go, the more we realize that certainty is often an illusion we cling to, and reality itself behaves more like a well-informed guess. The Monty Hall paradox looks simple, but our instincts make it confusing. You stand in front of 3 doors. Behind one is a prize. You choose a door. The host, who knows where the prize is, opens a different door and shows you it's empty. Then he gives you a choice. Stay with your original door or switch to the remaining one. Most people stay. It feels fair. 2 doors remain, so it seems like a 50-50 chance. But switching doubles your chance of winning. This result feels wrong because our intuition ignores the structure of the situation. At the start, you have a 1 in 3 chance of picking the prize. That means your choice is wrong 2 out of 3 times. When the host removes one losing door, he doesn't create new odds. He reveals part of the original structure. If your first pick was wrong, which happens most of the time, the prize must be behind one of the other 2 doors. When he opens a door that isn't the prize, he is squeezing that 2/3 probability onto the one remaining closed door. Switching captures the 2/3 chance you gave up when you first guessed. Staying holds on to the original 1/3. That's why switching is better. Many people resist this explanation because they frame it as a fresh decision after information has been revealed. We think the situation resets once we see an empty door. But the host is not picking a random door to open. He always shows a door without the prize and never opens your door. His action is not passive, it carries information. The game is not symmetric, even though it looks that way after the reveal. Framing the problem differently helps. Imagine 100 doors instead of 3. You choose 1 door. The host opens 98 losing doors. Only 2 remain, your original choice and 1 other. Would you stay? Almost everyone would switch. The reason is clear now. Your first pick had a 1 in 100 chance of being right. The remaining door holds all the probability from the other 99 doors, except the ones the host showed are empty. Switching now feels obvious. Shrinking the scenario to 3 doors hides that logic, but the math stays the same. Another way to see it is through repetition. If you played this game 300 times and always stayed, you would win about 100 times. If you always switched, you would win about 200 times. Real experiments have confirmed this over and over. The paradox persists not because the math is tricky, but because our intuition treats the host's action as random. In many games, revealed information does not change the odds, but in this one, the host's knowledge and intention matter. Our brains love fairness. 2 doors mean equal chances. At least that's how it feels. But fairness in probability does not mean symmetry in appearance. It means following the rules of the situation. The rules here favor the door you did not pick. The host's behavior shapes the outcome. Intuition often ignores hidden rules because they aren't obvious at a glance. The paradox also shows how poorly we handle conditional probability. We are comfortable with simple choices, but struggle when later actions depend on earlier ones. The host's choice depends on your first guess, and this dependence alters the odds. Even when people see the logic, it still feels wrong. Emotion and instinct resist the conclusion. This gap between feeling and fact is what makes the Monty Hall problem famous. The paradox teaches humility. It reminds us that some problems require stepping back instead of trusting the first instinct. It also shows that probability is not about what seems fair. It is about structure. If the host acted differently, the solution would change. If he sometimes opened the prize by mistake or picked a door at random, then switching wouldn't always be better. The advantage only exists because the host's actions follow strict rules. Understanding those rules is key. Think about a different example. Suppose the host always opens a random door that you didn't choose, regardless of whether it holds the prize. Sometimes he accidentally reveals the prize. In that version, switching does not help. The structure changes, so the math changes. This proves the original result depends on the host's strategy, not just the number of doors. Our intuition fails because it overlooks the host's knowledge. Probability demands clarity about what information is revealed and why. The Monty Hall effect shows up outside of game shows. In decision-making, we often stick with initial choices because of commitment or pride. We feel safer staying put. Switching feels like admitting we were wrong, but in many situations, investing, diagnosing, strategizing, new information changes the landscape. Probability encourages us to update our decisions. Intuition tells us to stay loyal to the first pick. Real life often rewards switching. The paradox also applies to search problems. Say you're looking for your keys in your house. You check one room. Someone tells you the keys are not in another specific room. Should you go back to your first room or search the third one? The third room is more likely because the first choice was random and the new information eliminates another option. The situation mirrors Monty Hall. The logic is the same. But in everyday life, we don't label it as probability. We just call it searching smarter. There's also a psychological layer. People dislike feeling manipulated, and the Monty Hall game feels like a trick. The host knows more than you do. That imbalance of information makes people defensive. They assume switching is a trap. This emotional response blocks logical thinking. The paradox is a perfect example of how intuition can protect ego at the cost of accuracy. When we reframe the problem with many doors or run experiments, intuition begins to align with math. But without that shift, the mind clings to symmetry. This shows how framing shapes understanding. The right perspective makes the answer obvious. The wrong one keeps us stuck. The Monty Hall paradox is more than a math puzzle. It is a mirror that shows how stubborn our thinking can be. It reveals the gap between feeling and fact, and how probability often lives in that gap. Switching doors feels wrong because our brains prefer simple fairness. But when we respect structure over instinct, the truth becomes clear. Switching doubles your chance. Sometimes information is more powerful than action. The Monty Hall problem proves it. Nothing physically changes after the host opens a door. The prize never moves. The doors stay in place. Yet the moment the host reveals a goat, the game shifts in a way most people don't notice. Why? Because the host knows where the prize is, and that knowledge shapes what he reveals. His action looks simple, but it carries information. That information changes the odds. At first, you choose one of 3 doors. Your chance of being right is 1 in 3. The other 2 doors together hold a 2 in 3 chance of being correct. Then the host, who knows the prize's location, opens a door you didn't pick and shows you it's empty. This is not random. He never accidentally reveals the prize. He is filtering information. When he does this, he is not just removing a door. He is telling you something about the distribution of probability. 2 in 3 chance from the unchosen doors does not disappear. Instead, it concentrates onto the one unopened door he did not touch. Staying keeps your original 1 in 3 chance. Switching gives you the combined 2 in 3. Nothing physical moved. only knowledge shifted the outcome. This idea feels strange because we usually think probability is tied to physical objects. If nothing moved, why should the odds change? But probability is not only about objects, it is about what we know. The structure of uncertainty shifts when someone with knowledge takes an action that depends on that knowledge. This is called conditional probability. The condition is the host's rule. He will always open a losing door. That rule is what changes everything. Imagine a different version of the game. The host does not know where the prize is and randomly opens a door. Sometimes he will accidentally reveal the prize. In that version, the moment he opens a goat door, you gain no information about your original pick. The odds actually become 50-50. The math changes because the host's choice was not informed. Same physical result, a door opened and a goat shown, but the meaning of the action changes because the intention behind it changes. The difference is knowledge. This principle reaches beyond game shows. Consider medical testing. If you randomly test a group of people for a rare disease and someone tests positive, the probability they truly have the disease depends not just on the test result, but on how the test was designed and what the tester knows. A test that always avoids false positives carries more meaning when it says positive than a test that does not. Two identical results can carry different weight depending on knowledge, method, or intent. Think about searching for something. Suppose you lost your wallet at home. You check the living room and don't find it. That search changes your knowledge. The wallet didn't move. Nothing physical changed, but probability shifted. Now the living room has a near zero chance, and other rooms have higher chances. The house is the same, but your information reshapes the odds. In everyday life, people often ignore how much knowledge influences outcomes. In poker, a player who understands another player's tendencies can make better decisions than someone with the same cards but no insight. Cards are physical, behavior is physical, but knowledge about patterns changes the quality of choices. Probability bends around information. The same thing happens in legal trials. Two people might hear the same evidence, but a lawyer who understands how juries think can frame that evidence in ways that shift interpretation. The facts stay the same, but the meaning of the facts changes based on what people know and how they use it. Outcomes are shaped by information, not only by events. Even memory works this way. When you learn new information about a past event, your understanding of that event changes. The past does not change, but your interpretation does. Your brain rewires the story based on what you now know. The same event can feel different depending on what context you add. Knowledge reframes reality. The Monty Hall problem exposes how deeply we tie fairness to symmetry. After the host opens a door, most people see two doors and think equal odds. But symmetry is broken by knowledge. The host did not pick a door at random. He selected it based on the prize's location. That knowledge creates bias in the structure of the game. Probability depends on process, not just outcome. When the process uses hidden information, the result carries weight that intuition misses. Think of a police officer telling you, "We already ruled out suspects A and B." Even if A and B were innocent, the statement tells you they were considered for valid reasons. The remaining suspect now looks far more likely. The officer did not arrest anyone. Nothing changed physically, but the elimination process was informed, and that knowledge directs suspicion. Information can behave like force. It pushes probability around. It collapses possibilities. It makes certain paths impossible and others more likely. In quantum physics, a particle exists in many possible states until observed. Measurement causes the wave function to collapse into a single outcome. The act of knowing changes the system. The parallel to Monty Hall is not perfect, but the spirit is the same. Observation and intention matter. Even trust works this way. If someone tells you, "You can believe me," that statement is less meaningful than when someone you already trust says nothing at all. The value of information comes from who delivers it and why. The same words can carry different probabilities depending on the source. Knowledge is not neutral. It comes wrapped in context. We often judge outcomes without asking how the information was produced. Two companies might both claim that a product is safe. If one did deep testing and the other just guessed, the statements look the same but mean different things. The math behind risk changes based on process, not just conclusion. Monty Hall is one of the clearest examples of how information shapes probability, but the lesson is everywhere. When someone reveals something deliberately, they are doing more than showing. They are guiding. When someone hides something, they are doing more than withholding. They are manipulating possibility. Knowledge is power, not because it controls objects, but because it controls expectations. In life, we often cling to what feels even or simple. We like to believe that if nothing physical changes, nothing else has shifted. But that view ignores how minds work. The host's knowledge in Monty Hall reminds us that information itself behaves like an invisible hand. It tilts the game board. Reality is not just about what exists. It is about what is known, by whom, and when. The laws of probability depend on structure, and structure depends on knowledge. The host opens one door, nothing moves, and yet everything changes. The birthday paradox surprises almost everyone the first time they hear it. You gather just 23 people in a room, and the odds that at least 2 of them share a birthday are already over 50%. That seems impossible. There are 365 days in a year. How could 23 people be enough to create a better than even chance of a match? Most people expect the number to be much higher, maybe 100 people or more. The paradox doesn't come from the math being strange. It comes from the way we frame the problem. When people first hear the question, they quietly compare each person to the entire calendar. They think, what are the odds someone shares my birthday? That chance is small, only 22 chances out of 365. But that's not the real question. The puzzle is not about one person matching everyone else. It's about any 2 people matching each other. Those are different problems. The key is to count pairs, not individuals. With 23 people, there are many possible pairs. In fact, there are 253 unique pairs of people in a group of 23. Each pair has a chance to share a birthday. One pair is unlikely to match, but with 253 pairs, the chances pile up. Randomness doesn't work the way our intuition expects. We often think in straight lines. Probability works in combinations. Instead of calculating the chance of a shared birthday directly, it's easier to calculate the opposite, the chance that no one shares a birthday. Start with the first person. Any birthday works. The second person must have a birthday different from the first. That's 364 out of 365 possible days. The third person must avoid the first 2 birthdays. That's 363 out of 365. Keep going. Multiply these probabilities. 364 over 365 times 363 over 365 times 362 over 365 all the way down to 343 over 365. The result is about 0.492. That means there's a 49.2% chance that everyone has a unique birthday. Flip it, and the chance of at least one shared birthday is about 50.8%. That's how the paradox holds. The math is correct. The surprise comes because our minds are not built to think in exponential possibilities. We focus on the individual instead of the group. We underestimate how fast combinations grow. This mistake shows up in many parts of life. We underestimate risks in large systems. We assume rare events stay rare, even when the number of opportunities is enormous. The birthday paradox is not just a cute puzzle. It's a warning about intuition. Consider lotteries. The odds of any one person winning are tiny, but with millions of players, someone wins frequently. People call it luck or fate, but it's just probability at scale. The birthday paradox helps explain why rare things happen more often than we expect when enough chances exist. Think about data security. In hashing systems, a collision happens when two different inputs produce the same output. Well-designed systems make collisions rare, but if a system has too many users or entries, collisions become more likely. This is known as the birthday attack in cryptography. Hackers use the same logic as the birthday paradox to find weaknesses. You don't have to match one specific value. You just need any two values to match. The paradox also appears in social life. Think about coincidences. You meet someone with the same birthday, hometown, or favorite movie. It feels magical. It feels like the world is small. But in a large enough group, coincidences are guaranteed to happen. They only surprise us because we look at them backwards. We notice the match after it appears and assume it was extremely unlikely. But the number of possible coincidences is much higher than we realize. Even in everyday conversations, patterns pop up that follow the same logic. Someone brings up a topic, and suddenly another person mentions the same thing. It feels like synchronicity. But with enough people talking about enough things, overlaps are bound to happen. Our intuition pays attention only to the hits, not the countless near misses. The birthday paradox also reveals how framing influences fairness. If someone asked, "How many people do you need in a room until everyone has the same birthday?" the answer would be 366. That aligns with our intuition. But how many people until any two share a birthday feels similar, yet the answer is radically smaller. This gap between what feels similar and what is mathematically different shows how context shapes understanding. It also teaches humility. Our brains like simple patterns and linear progressions. Probability often grows in curves. Combinations sneak up on us. What looks unlikely becomes likely faster than we think. The birthday paradox is a gentle way to demonstrate this deeper truth. Our instincts about chance are often unreliable. To push this paradox further, consider larger groups. With 50 people, the chance of a shared birthday is about 97%. With 70 people, it's over 99.9%. By the time you reach 100 people, it's almost guaranteed. Once again, nothing mystical is happening. The number of pairs keeps growing. A group of 100 people has 4,950 possible pairs, nearly 5,000 opportunities for a match. Probability loves large samples. What makes the birthday paradox powerful isn't just the result, it's the way it flips our expectations. It shows how easily we can be misled by surface-level thinking. It invites us to step back and look at problems from the right angle. When we do, things that looked unlikely become obvious. Patterns in life often follow the same logic. When we focus on individuals, events seem random. When we zoom out to the group level, structure appears. We might look at one failure and feel unlucky, but across many attempts, luck fades and probability takes over. Success in careers, sports, or business often depends less on single events and more on the number of tries. The birthday paradox reminds us that scale changes everything. Even fairness takes on a new meaning through this lens. We often think fairness means every outcome should feel evenly spread, but probability doesn't care about feelings. It cares about structure, volume, and combinations. Fairness in probability means following consistent rules. It does not mean matching our intuition. The birthday paradox is more than a quirky statistic. It's a doorway into a better understanding of probability itself. It teaches us to ask deeper questions, to look beyond first impressions, and to respect the tower of many small chances piling up. It shows us that reality often hides complexity behind simple appearances. Our minds think in straight lines, but the world often curves. Our intuition handles simple probabilities well. Flip a coin, and we know there's a 50-50 chance of heads or tails. Roll a die, and we know each number has a 1 in 6 chance. Linear cases feel natural, but probability does not always grow in straight lines. When combinations enter the picture, the math scales non-linearly, and our intuition breaks. The numbers grow faster than our instincts can follow. What looks unlikely often turns out to be likely. What feels fair often isn't. The deeper we go into combinations, the more our mental shortcuts lead us astray. The birthday paradox is the most famous example. Ask people how many individuals are needed in a room before there's a 50% chance to share a birthday. Most guess 50 or 100. The correct answer is 23. This shocks nearly everyone. The mistake comes from comparing each person to the 365 days in a year. But the problem isn't about one person matching the group. It's about any pair matching each other. In a group of 23 people, there are 253 unique pairs. Each pair has a chance to match. That's where the odds come from. Our brains focus on people. Probability focuses on pairs. The number of pairs rises much faster than the number of people. Combinations explode quietly. This nonlinear growth appears everywhere. In a group of 50 people, there are 1,225 pairs. By 100 people, there are 4,950 pairs. The number of comparisons grows roughly with the square of the size of the group. That's why coincidences are common, even when individual odds are small. We notice the coincidences, but ignore how many opportunities there were for them to appear. We think in single threads. Probability works across networks. This flaw damages our judgment in real life. When something rare happens twice in a row, like 2 lottery winners from the same town, we scream conspiracy. But millions of people play. There are thousands of towns. Eventually, strange repeats become inevitable. Rare events are not rare when chances multiply. Nonlinear probability makes the impossible almost guaranteed given enough attempts. Intuition can't see that scale. Combinations also mislead us in expectations. When we think about rolling 2 dice, many assume each total from 2 to 12 is equally likely. But there is only one way to get 2, 1 plus 1. while there are 6 ways to get 7. The number of combinations matters more than the surface outcome. 7 is the most likely total, not because of luck, but because of structure. Probability hides in paths, not just results. In card games, players often underestimate the chance of certain hands. The probability of drawing a specific card from a deck is straightforward. But when we ask about drawing any ace or any pair, combinations take over. The number of ways to choose becomes the key factor. That's why games like poker rely on combinatorics. Experts think in combinations. Beginners think in sequences. The difference separates luck from skill. Our misunderstanding also affects risk. If a plane crash has a 1 in a million chance, that sounds safe. But if a million planes fly each year, the probability someone crashes becomes high. Multiply low probability by many trials, and the outcome becomes expected. Probability scales non-linearly with volume. Intuition forgets to multiply. Even everyday patterns fool us. Someone says, "What are the odds I ran into this person twice in 1 week?" It feels unbelievable. But how many people did they not run into? How many places did they visit? How many interactions occurred? We focus on the hit and ignore the misses. Combinatorics accounts for every possible pairing, not just the one that grabbed our attention. Coincidences are the visible tip of a huge structure of possibilities. The human mind simplifies. It wants one cause, one effect, one outcome. But combinations create layered possibilities that interact. In the Monty Hall problem, staying feels 50-50, but switching gives you a 2/3 chance. Why? Because there are 3 possible setups, and 2 of them reward switching. Again, combinations determine probability, not surface appearance. We look at the 2 remaining doors and assume symmetry. Probability looks at the entire structure and sees imbalance. In social networks, combinations grow even faster. If each person connects with just a few others, the total number of relationships in the network skyrockets. That's why rumors spread fast and why viral trends appear unpredictable. The number of possible paths a message can take becomes enormous. Simple local actions create complex global outcomes. Intuition gives up because it can't grasp exponential growth. Think about decisions with multiple choices. If you have 5 options for breakfast, and 5 for lunch, and 5 for dinner, that's 125 daily combinations. Add snacks and drinks, and it skyrockets. Planning becomes overwhelming, not because each choice is hard, but because the combinations multiply. Complexity doesn't come from depth, it comes from branching. In cybersecurity, this principle shows up in brute force attacks. A password with 10 digits from 0 to 9 has 10 billion combinations. Add letters and symbols, and the combinations explode. Each extra character multiplies the total possibilities, not adds. That's why strong passwords depend on length and variety. The defense comes from nonlinear growth. Nonlinear probability also affects group dynamics. Suppose 10 people each make 1 decision per day. After a week, that's 70 decisions. But the effect of those decisions interacting with one another creates thousands of possible group outcomes. This is why predicting behavior at scale, markets, politics, culture, is incredibly hard. Each individual is simple. The combinations between individuals create chaos. We also see this in genetics. A child inherits traits from both parents, but the combinations of genes create massive diversity. Siblings share parents, yet look and behave differently. DNA doesn't mix in a straight line. It combines in countless ways. Small changes in combination produce large changes in outcome. Our intuition prefers linear cause and effect. When a system behaves unpredictably, we assume someone must be controlling it or the system must be flawed. In reality, nonlinear combinations create complexity naturally. What looks like randomness often comes from too many interacting variables. The structure is there, we just can't see it in our heads. Probability forces humility. It reveals the limits of intuition. It reminds us that scale changes truth. What is rare for one trial becomes common across many. What feels fair on the surface hides imbalance underneath. When we fail to account for combinations, we fall for coincidences, misunderstand risk, misjudge fairness, and draw the wrong conclusions. To think clearly, we must learn to see beyond the individual outcome and recognize the multiplying power of possibilities. The gambler's fallacy is one of the most common mistakes we make when thinking about probability. It happens when we believe that past random events change future outcomes, even when each event is independent. A classic example is flipping a coin. If it lands on heads 5 times in a row, many people think tails is due, but the coin has no memory. The chance of tails on the next flip is still 50%. Each flip is separate. The streak feels meaningful, but it has no influence on the next result. This fallacy shows how our intuition clashes with randomness. We expect patterns to balance quickly. We believe fairness means results should even out in the short term. But probability does not promise balance over small samples. It only balances over very large numbers of trials. A coin might land on heads 10 times in a row and still be fair. That outcome is unlikely, but not impossible. Randomness is messy. It clumps. It streaks. Our brains don't like that, so we force order where there is none. Casinos exploit this instinct. Picture a roulette wheel. It spins and lands on red 8 times in a row. People crowd the table and bet on black, confident that black must come next. But each spin is independent. The wheel does not correct itself. The chance of red or black remains the same as always. Yet gamblers convince themselves the universe is out of balance. They treat the wheel like a moral system, not a random one. This mistake is so powerful that it once caused financial disaster. In 1913, at a casino in Monte Carlo, the roulette wheel landed on black 26 times in a row. Gamblers kept betting on red, pouring in money each spin, believing the streak had to end. They lost fortunes. The streak eventually did end, but not before destroying many players. The longer the streak went, the more confident people felt, when in reality, the odds never changed. The gambler's fallacy also shows up in everyday thinking. Someone says, "I've had bad luck all day. Something good must happen soon." But luck does not run on a schedule. Random events don't queue up to stay balanced. The future does not compensate for the past. The universe is not keeping score. Even sports fans fall into this trap. A basketball player misses 5 shots in a row. Fans say he's due for a make, but unless something about his ability changed, the chance of making the next shot is based on his skill, not his streak. In reality, long stretches of misses or makes often happen in purely random sequences. We label them hot or cold, but sometimes they're just noise. The fallacy appears in reverse too. After several losses, people think they must be on a cold streak and give up, even when odds remain unchanged. They assume the past defines the future. They build emotional stories around randomness. Instead of seeing chance, they see momentum. This leads to poor decisions because they're reacting to patterns that aren't real. Part of the problem is that we confuse independence with dependency. Some events truly do affect future outcomes. Drawing cards from a deck without replacement changes the odds with each card removed. If 5 cards have been drawn and none were aces, The chance of the next card being an ace has increased because fewer cards remain. Here, the events are dependent, but in coin flips, dice rolls, and roulette spins, each event resets. There is no memory. When people treat independent events like dependent ones, the gambler's fallacy takes over. This mistake comes from how we think about fairness. We assume that a random sequence should look balanced in the short term. We think that in 10 coin flips, we should get something close to 5 heads and 5 tails, and any long streak feels suspicious. But randomness does not care about distribution in small samples. True randomness often looks more uneven than our minds expect. In fact, perfectly alternating heads and tails would be less random than a streak. Our brains look for patterns because patterns help us survive. When something repeats, we search for meaning. In many cases, that instinct is useful, but randomness produces patterns too, and those patterns do not always mean anything. The gambler's fallacy mistakes noise for significance. It gives purpose to coincidence. Probability teaches us how to think beyond instinct. Instead of focusing on what just happened, we focus on the structure of the process. If the process produces independent events, like coin flips, roulette spins, or slot machine pulls, then past outcomes do not influence the future. The only thing that matters is the rule of the process, not the history of results. The gambler's fallacy also reveals how we struggle with large numbers. Over many trials, results do trend toward expected averages. This is the law of large numbers. But people confuse this law with the idea that outcomes must balance quickly. They think if heads appears repeatedly, tails will appear soon to catch up. But the law only works over thousands or millions of trials, not in the next few. Randomness does not self-correct. It just averages out over time. This misunderstanding can lead to real harm. In financial markets, investors sometimes hold on to losing positions, believing a rebound is due. Or they chase a winning stock, thinking momentum will continue forever. In both cases, they rely on patterns instead of sound analysis. The fallacy blinds them to actual risk. It also affects personal behavior. People in bad situations convince themselves things will improve simply because things have been bad for a while. Hope is valuable, but confusing probability with karma can be dangerous. Improvement comes from change, not from the length of the struggle. The gambler's fallacy teaches humility. It reminds us that the world does not revolve around our expectations. Randomness has no memory. Fairness does not guarantee comfort. Some outcomes cluster. Some streaks last. Probability does not bend to emotion. It follows structure. But the fallacy also teaches clarity. Once we understand independence, we can make better choices. A fair coin remains fair no matter how many heads came before. A die roll stays 1 in 6 no matter what was rolled last. A random process stays random, regardless of streaks. Knowing this helps us avoid traps and focus on what truly influences outcomes: skill, structure, and strategy. To beat the gambler's fallacy, we must separate feelings from facts. We must ask, do past events affect future odds in this situation? If the answer is no, then every new event is fresh. If the answer is yes, then we should adjust based on the rules, not on streaks. Understanding the difference turns confusion into clarity. Randomness is not out to balance itself. It just flows. Past events don't owe us anything. The wheel doesn't care. The coin doesn't care. And the sooner we accept that, the smarter we become. Simpson's paradox is one of those ideas that looks impossible until you understand how it works. It happens when a trend appears in separate groups, but disappears or even reverses when those groups are combined. The data doesn't change, but the way it is grouped does, and that grouping changes the story. The paradox teaches us that statistics are not just about numbers. They're about context, structure, and how data is organized. When we ignore those parts, we draw the wrong conclusions with complete confidence. Imagine two hospitals. In each hospital, a medical treatment works better than the alternative. Hospital A gives the treatment to very sick patients and sees a 70% success rate with it, and 60% without it. Hospital B treats mostly mild cases and sees 90% success with the treatment and 80% without. In both hospitals, the treatment is better, but when we combine the results from both hospitals, the overall success rate might show that the treatment performs worse. How is that possible? Because the treatment was used more often on harder cases. The combined data hides the fact that different patients were treated in different settings. The group sizes and underlying conditions matter as much as the raw percentages. This is the core of Simpson's paradox. Averages are not always honest. When data from different groups is blended, the groups may carry different weights. One group may have many more cases than another. One group may be much more difficult. The combined result is influenced by these weights. Without noticing, we let the large or difficult group dominate the overall average. The trend we see is real, but it answers a different question than we think. Consider a simpler numerical example. A baseball player has a batting average of .300 in the first half of the season and .250 in the second half. Another player has .280 in the first half and .260 in the second half. In both halves, the first player is better. But suppose the first player only had 10 at-bats in the first half and 200 in the second. The second player had 200 at-bats in the first half and 10 in the second. When you combine the numbers, the second player might now have the higher overall average. The performance didn't change, the weight of the attempts did. The paradox exposes how easy it is to mislead ourselves with partial information. This paradox appears in real-world debates. In university admissions, a school might admit a higher percentage of women than men in each department. But overall, the total admissions might show a lower percentage of women being accepted. Why? Because women may have applied in greater numbers to the more competitive departments with lower acceptance rates. The combined data makes it look like bias against women. The department data shows the opposite, which is correct. Both are true in different frames. The paradox reminds us to ask, what is being measured? At what level? Simpson's paradox warns us that data alone is not enough. The meaning depends on grouping, and grouping depends on judgment. Without careful thinking, we see patterns that don't exist or miss patterns that do. When trends flip, we assume the data is wrong, but the data is fine. We're just looking from the wrong angle. Another famous example comes from criminal justice. Two lawyers might each win a higher percentage of their cases against a certain prosecutor in separate districts. But when you merge the cases from both districts, the prosecutor might appear to win more often overall. The difference comes from the number of cases tried in each district. One district might give easy cases to the prosecutor and hard cases to the lawyers. When combined, the easy wins for the prosecutor outweigh the hard losses. The paradox reveals that the overall comparison hides the conditions of each group. Simpson's paradox also shows up in medicine, sports, hiring data, public policy, and even everyday personal decisions. It reminds us that correlation does not always mean what we think it means. A trend in one setting may depend on hidden factors like difficulty, opportunity, sample size, or selection bias. When those hidden factors change, the trend shifts. The deeper lesson is that fairness and performance cannot be judged from a single layer. Two people might both improve in their own categories, but when combined, one might look worse. For example, A student might raise their grade in both math and science. But if science is weighted far more in the final score, the overall grade might drop. The student did better in both subjects, but the structure changed the final result. This feels unfair at first, but it reveals how weighting shapes outcomes. Simpson's paradox forces us to ask new questions. Are these groups comparable? Should we combine them? What are the hidden variables? Are we measuring individuals or environments? When data reverses, it is not lying, it is pointing to complexity beneath the surface. Even in simple daily life, this paradox applies. Suppose you exercise 2 days. On day 1, you walk 3 miles in 30 minutes. On day 2, you run 1 mile in 8 minutes. On both days, your pace improved in parts of your workout, but your total time might make it look like you got slower overall. The parts improved. The whole looks worse. The structure changed how we see progress. People often misuse statistics because they trust the overall average without checking the groups. This creates false narratives. A product looks worse overall, even though it performs better in every category. A company looks biased, even though it treats every group fairly within departments. The error is not in the data, it's in how it is sliced. Simpson's paradox does not mean statistics are unreliable. It means context matters. It means simple comparisons can mislead. It means data tells different stories depending on how you organize it. When we ignore subgroup differences, we blur important distinctions. When we overfocus on subgroups, we might miss the larger trend. The paradox lives in the tension between these views. The real power of Simpson's paradox is that it humbles us. It shows that intuition, logic, and even surface data can all agree and still be wrong when seen from a higher level. It reminds us that explanations need structure, not just numbers. The truth is layered. Sometimes the small picture is clearer than the big picture. Sometimes the big picture reveals what the small picture hides. The challenge is knowing which lens to use. Bertrand's paradox is a powerful reminder that even when a problem looks precise, the meaning of random can change everything. The paradox comes from a simple question. If you draw a random chord in a circle, what is the probability that the chord is longer than the side of the inscribed equilateral triangle? It sounds like there should be one clear answer, but depending on how you define random chord, you can get different probabilities: 1/3, 1/2, or 1/4. All methods look reasonable. All are mathematically correct within their own definitions, yet they disagree. The paradox exposes a deeper issue. Probability does not work without a clear description of the process behind the randomness. At first, this seems strange. If something is random, shouldn't the outcome be unique? But randomness isn't just about unpredictability. It's about the method used to generate outcomes. If different methods define random in different ways, the results will differ. The paradox lives in that gap between assumption and definition. Let's explore the 3 classic methods. In the first method, you pick 2 random points on the circle and draw the chord between them. This feels natural. Using geometry, it turns out that only 1/3 of these chords are long enough, so the probability is 1/3. In the second method, you pick a random point inside the circle and draw the chord perpendicular to the radius through that point. If the point is within a certain distance of the center, the chord will be long enough. Here, half of the chords qualify. The probability becomes 1/2. In the third method, you choose a random angle and a random distance from the center along some fixed radius to determine the midpoint of the chord. In this setup, only 1/4 of the chords are long enough. Now the probability is 1/4. 3 different answers for the same question. Which one is right? The paradox is that each answer is valid under a different interpretation of random. The geometry didn't change, the circle didn't change, only the process changed. This breaks our intuition because we think probability is absolute, but probability always depends on a model. If the model is ambiguous, the probability is ambiguous. Think of it like shuffling a deck of cards. If you physically shuffle, many outcomes are possible. But if you always shuffle the same way, you might create predictable patterns. The word shuffled hides the process. Random chord hides the process too. Without specifying the steps, we don't know what distribution of chords we are using. Bertrand's paradox exposes that hidden structure. This paradox also appears in real-world problems. In physics, when modeling gas molecules, you need to define how positions and velocities are distributed. If you pick the wrong assumption of randomness, the predictions fail. In statistics, sampling methods matter. If you say a survey selects people at random, but only uses phone numbers from landlines, it isn't truly random. The sampling method changes the results. The same data question can yield different answers depending on how randomness is applied. Bertrand's paradox forces us to separate two ideas: unpredictability and uniformity. Something can be unpredictable without being uniformly distributed. In the chord example, choosing two random points on a circle treats all boundary points as uniform. Choosing random midpoints treats all internal positions as uniform. But the mapping between those two spaces is not equal. Uniform on the edge is not uniform in the middle. Because geometry distorts distances and areas, equal randomness in one space does not mean equal randomness in another. This is why defining randomness is not trivial. The word hides decisions about symmetry, density, and dimension. In probability theory, those decisions are formalized using measure theory. But Bertrand's paradox gives us a simple demonstration of why those tools are needed. Without them, we get contradictions. People often assume that the most intuitive method is the correct one, but intuition depends on perspective. If you think of a chord as defined by two endpoints, you get one answer. If you think of a chord as defined by a midpoint and a direction, you get another. In some contexts, the first makes more sense. In others, the second is more natural. The problem is not in the math, it's in the question. This paradox also teaches us something deeper about fairness. We often assume that chance is neutral, but chance can be rigged by structure. If you define randomness poorly, you can produce biased results without intending to. For example, imagine asking a computer to generate random points on Earth. Should it pick random latitudes and longitudes directly? That method places too many points near the poles because lines of longitude get closer together. To create truly uniform distribution on a sphere, you need a specific method. Random isn't enough. You need random with respect to area. Without that detail, you get Bertrand's paradox in disguise. In everyday life, this plays out in subtle ways. When someone says two groups are randomly assigned, we assume fairness. But if the selection pool has hidden structure, different demographics, different sizes, different access, the assignments might appear random, yet produce skewed outcomes. The method matters more than the label. Bertrand's paradox is also a warning about language. Natural language compresses complex ideas into simple terms. We say random, fair, balanced, even, and assume everyone hears the same thing. But under the surface, these words hide assumptions. Probability doesn't work with vague language. It works with precise definitions. Without them, we get paradoxes. Even the paradox itself doesn't offer a single correct answer. Instead, it forces us to ask, what definition of random fits the real-world process we care about? If a physical process selects chords in a certain way, our model of randomness should match that process. In some cases, the 1/2 method is appropriate. In others, 1/3 might reflect reality. There isn't one truth. There are multiple truths based on the rules. This is not a weakness of probability, it is a strength. It reminds us that probability is not magic, it is a tool. Like any tool, it must be used with clarity and precision. Bertrand's paradox shows that if we skip that step, we can produce convincing answers that contradict each other. At first glance, the question, "What is the chance a random chord is long enough?" sounds specific, but it is incomplete. The hidden power of the paradox is that it doesn't just show different results. It reveals why the question fails. It teaches us that before solving a problem, we must understand the process behind it. Probability does not live in outcomes. It lives in the method that produces them. Bertrand's paradox captures a simple truth. In probability, definitions are destiny. Probability doesn't just measure what might happen in the future. It also measures how confident we are about something, even if it has already happened, but we don't know the result yet. That means probability can change when new information arrives, not because the world changed, but because our knowledge did. Many people find this confusing. They think probability must be fixed once an event occurs. But probability is about belief under uncertainty, not just outcomes. Imagine a coin flip that already happened. The coin is covered. You don't know the result. What is the probability it is heads? You would probably say 50%. Now someone tells you they heard it land, and it didn't sound like tails. Suddenly, your belief changes. Maybe you adjust to 70% heads. Did the result change? No. The flip was already done. Probability doesn't describe the coin. It describes your knowledge about the coin. Let's look at a more familiar case: sports. A basketball game ends while you're at work. You haven't seen the score. Before checking, you might believe your favorite team had a 60% chance of winning. Then your friend texts, "Crazy comeback." That changes your belief. Maybe now you think the team won with 80% probability. The actual result was fixed hours ago, but your probability shifted. That's not inconsistency. It's Bayesian reasoning in action. New information updates your belief. This becomes even clearer with the famous Monty Hall problem. At the start, each door has a 1 in 3 chance of hiding the prize. You choose one door. The host opens another door and shows it's empty. The prize hasn't moved, but your probability changes. The unopened door now holds a 2 in 3 chance. Nothing physical changed, only information changed. The host's knowledge reveals structure. Probability reacts to that new structure. Some people struggle with this because they confuse probability with fate. They assume probability measures physical uncertainty, but probability measures our uncertainty. The universe doesn't use probabilities, we do. Think about this scenario. Someone places a ball in one of 3 boxes while you're out of the room. You return and guess which box it's in. The ball is already placed, but for you, the probability is still 1 in 3. If someone secretly peeks and tells you it's not in box A, your belief changes. The event already happened, but your updated probability becomes 1 in 2. If the person telling you this knows where the ball is and deliberately avoids giving full information, like Monty Hall, the probability might even shift to 2 in 3 for box C. It all depends on the source and nature of the information, not the event itself. This is why probability feels slippery. It attaches to knowledge, not time. The key is understanding conditional probability. Given X, what is the chance of Y? If X changes, the answer changes. That holds even if Y already occurred. Without the condition, probability floats in uncertainty. The medical world uses this reasoning every day. Imagine a disease that only 1% of people have. A test is 99% accurate. If you test positive, you might think there's a 99% chance you're sick, but that's wrong. You must update based on base rates. Out of 10,000 people, 100 actually have the disease. The test correctly identifies about 99 of them, but it also produces around 99 false positives. So when you test positive, the probability you're actually sick is about 50%. Learning this test result changes your belief from 1% to 50%. The event, whether you have the disease, was already true or false before the test, but you only adjusted your belief after new information arrived. Bayesian thinking is how we refine our understanding as evidence appears. It's how detectives solve cases, doctors diagnose, investors react, and humans learn. The event does not need to be in the future. Probability is about uncertainty, and uncertainty exists in past, present, or future events. Consider drawing cards. You shuffle a deck and place the top card face down. What's the chance it's an ace? 4 in 52. Now your friend, who saw the card, says, it's a high-value card. With that new clue, your probability might jump to, say, 12%. The card was always either an ace or not, but your view of the situation sharpened because someone gave you partial information. That shift makes you more accurate, not less, even weather forecasts follow this reasoning. Imagine a storm already formed offshore. Meteorologists don't know its exact track. The storm's path is physically set by atmospheric conditions, but as new satellite data arrives, they improve their predictions. The storm didn't change, the knowledge did. Now think about the phrase, the probability the team won. Some people argue this is meaningless once the game is over. But that phrase really means the probability I assign to the team having won based on what I know. This statement is valid until you see the result. Probability collapses to 0 or 1 only when the uncertainty is removed. Before that, probability lives in the mind. Consider another example. 2 envelopes contain money. One has twice as much as the other. You pick one at random and peek inside. You see $50. What is the probability the other envelope has $100? What is the probability it has $25? Your belief depends on the process used to fill the envelopes. Without knowing how they were filled, you can't assign clean probabilities. You need structure. Once you understand the rules, your belief changes. The money was already in the envelopes, but your probability updates when you learn the amount in yours. Again, the event is fixed. The belief is fluid. Many logical puzzles hinge on this concept. The classic two-child problem is a good example. A person says, I have 2 children and one is a boy. What's the probability the other child is a boy? Many say 50%. In reality, it's 1/3, assuming equal gender probability and that the statement was made without bias. But change the wording to, my older child is a boy, and now the probability becomes 1/2. The difference is information structure. The underlying reality didn't change, only the way the information was delivered. This shows how even small pieces of information can reshape probability. It also shows how flexible probability is. It's not fixed to events, it's tied to knowledge about events. Probability acts like a flashlight in a dark room. Before we turn on the light, we assign probabilities to where objects might be. When new information arrives, sound, memory, a glimpse, we update. The objects didn't move. The room didn't change. Only our understanding did. The better the information, the sharper the probability. In that sense, probability is not about predicting the future. It's about managing uncertainty. It helps us make better decisions with limited knowledge. When new information arrives, we don't cling to old beliefs. We update. That's not weakness, it's clarity. Probability lives in what we know, not just in what exists. Sometimes knowing less gives us a stronger sense of certainty. It sounds backwards, but it happens often. When we don't know all the details, our minds simplify reality. We compress possibilities into clean stories. We feel in control because we don't see the complexity. The moment we learn more, the world becomes messier. Outcomes feel less predictable, not because the world changed, but because our view widened. Think about sports. A casual fan might say, "Team A is better, so they'll win." It sounds confident, but someone who follows the sport closely might hesitate. They know about injuries, travel schedule, player fatigue, coaching strategies, matchup history, weather conditions, and even referee tendencies. With more knowledge comes more uncertainty. The casual fan sees one variable, strength. The expert sees dozens. The more variables you see, the harder it is to predict. Ironically, deep knowledge can make certainty disappear. This happens in investing. Beginners often think picking winning stocks is simple. Just buy the good companies. It feels obvious, but experienced investors hesitate. They know markets react to countless factors: interest rates, global news, investor psychology, earnings expectations, regulations. They understand randomness and volatility. They become cautious not because they know less, but because they understand how much they don't know. Ignorance creates illusion. It removes complexity and replaces it with clarity. If you flip a coin, you know it's 50-50. But if you study the physics of coin flipping, you learn that force, angle, spin, height, and air resistance all matter. The flip looks random because we don't track those variables. If we knew every variable perfectly, we could predict each flip, but we don't, so we call it random. Surprisingly, the less we know, the more comfortable we feel using probability. We accept 50-50 without question. Too much detail makes the problem harder, not easier. Consider decision-making. Someone says, "I'm going to start a business. If I work hard, it will succeed." They believe effort guarantees results. Their confidence comes from a simple model: hard work equals success. Someone with experience knows the truth. Timing, market demand, competition, cash flow, customer behavior, luck. Success depends on many things beyond effort. The experienced person feels less certain, not because they are less capable, but because they understand reality better. Even in memory, knowing less can make us more certain. Think about two siblings who remember a childhood event differently. Each is confident. They argue, but memory is unreliable. When new evidence appears, a photo, a message, a third person, they realize how much they forgot or misremembered. Before the new information, they felt sure. After, they feel unsure. More knowledge weakened certainty. Probability works this way too. When we think only in terms of what seems likely, we feel confident. But when we consider all the ways something can happen, we notice how many possibilities exist. For example, predicting tomorrow's weather feels easy to someone who just looks outside. It looks clear, it will stay clear. But meteorologists look at models, wind shear, humidity, pressure systems, shifting air masses. Their forecasts include uncertainty bands. More details allow better predictions, but also reveal instability. Knowing more exposes the limits of certainty. In daily life, we treat vague problems as simpler than they are. Someone says, "Just follow your passion." It sounds clear. But what if you have multiple passions? What if passion changes? What if passion doesn't pay bills? The simple advice feels predictable until you dig deeper. The more you understand, the more you see trade-offs and randomness. Sometimes knowing less lets us believe in fairness. If we only see results, we assume success comes from merit. But when we learn about hidden advantages, networks, timing, privilege, chance, we realize outcomes aren't purely earned. The world looks less predictable once we see the layers behind it. Even math can mislead when we oversimplify. Consider the average. If one student gets 100% and another gets 0%, the average is 50%. Without more information, we assume an average student is middle. But if we see the distribution, we realize there are no middle scores, just extremes. Less knowledge gives the illusion of balance. More knowledge reveals imbalance. In probability, this shows up in the idea of expected value. A lottery ticket might have an expected value of $1, but that doesn't mean you usually win $1. You almost always win nothing, and rarely win a lot. Ignorance of distribution makes outcomes seem predictable. Understanding distribution reveals uncertainty. Consider job interviews. Someone thinks the most qualified person gets the job. That feels predictable. But hiring also depends on chemistry, culture fit, timing, interview performance, and bias. The more you know about hiring, the harder it becomes to predict who will be chosen. Even language hides uncertainty. When someone says, "Studies show X," we feel confident. But if we read the study, we see margins of error, sample sizes, limitations, and assumptions. Before reading, we felt sure. After reading, we question. Information reduced confidence because it revealed nuance. This effect also appears in moral judgments. When we see only actions, we judge quickly. Someone yells, we think they're rude. But when we learn their context, stress, pain, loss, we become softer. Knowing less made their behavior look clear. Knowing more made it complicated. Sometimes knowing less protects us from anxiety. If we don't know about all possible dangers, we feel safe. Pilots understand everything that can go wrong in a plane. Passengers do not. The passenger relaxes. The pilot stays alert. One knows less and feels calmer. The other knows more and feels responsible. Complex systems make this especially clear. In ecosystems, economies, or social networks, small changes can create large effects. But if we don't see the internal connections, outcomes seem predictable. This caused that. In reality, many factors interacted. Without deeper knowledge, we believe in simple cause and effect. This illusion also affects problem solving. People often think they understand a topic well until they try to explain it. This is the illusion of explanatory depth. You think you know how a zipper works or how government works until you try to describe it. The moment you go deeper, uncertainty appears. You realize you knew only the surface. Before digging, the subject felt predictable. After digging, it becomes complex. Even hindsight creates a false sense of predictability. After something happens, we say, "I knew that would happen." But before it happened, we probably didn't. We rewrite our memory to make events seem obvious. We ignore all the other outcomes that could have happened but didn't. This selective memory gives us the illusion that we understand cause and effect. In reality, we compress complexity to protect our confidence. Knowing less narrows the world. It removes variables. It hides randomness. It makes outcomes feel clean, binary, and fair. Knowing more opens the world. It reveals hidden forces. It exposes unpredictability. It shows that small differences can lead to big changes. Certainty often comes from blindness, not wisdom. The more we learn, the more we see that outcomes depend on structure, chance, timing, and perspective. Our minds crave simplicity, but reality is layered. Sometimes our confidence drops, not because we are wrong, but because we are finally paying attention to how complex the world really is. Paradoxes are not always signs of error. Often, they appear when two or more valid perspectives collide. Each perspective makes sense on its own, but when compared, they seem to contradict. The clash is not about right versus wrong. It is about how truth can depend on framing, scale, information, or point of view. A paradox exposes the limits of a single perspective and forces us to look deeper. Consider the classic liar paradox. This statement is false. If the statement is true, then it must be false. If it is false, then it is true. Both perspectives, treating the statement as true or false, are logically valid starting points, but they loop into contradiction when combined. The paradox comes from applying rigid, true or false logic to self-referential language. The statement sits between categories. Language allows it, but logic resists it. Now think about motion through Zeno's paradox. He argues you can never reach a destination because you must always go halfway first, and halfway again, creating infinite steps. From the perspective of pure logic and infinite division, motion seems impossible. But from a physical perspective, motion happens easily. The paradox emerges because distance and steps represent different ways of viewing motion, continuous versus discrete. Each view is valid. Their clash creates the paradox. Probability offers similar cases. In the Monty Hall problem, one perspective says there are 2 doors left, so the chance is 50-50. Another perspective considers the entire sequence of events, including the host's strategy, and shows switching gives a 2/3 chance of winning. Both perspectives seem logical. One focuses on the moment, the other looks at the structure. The paradox appears only when intuition clings to the local snapshot, while probability lives in the full process. Simpson's paradox takes this even further. A treatment might perform better in each subgroup, yet worse overall when the groups are combined. Each subgroup tells one story. The total tells another. Both stories are true, depending on which level of analysis you use. The paradox arises because perspective changes the context of fairness and accuracy. Should we judge per group or across the entire population? The answer depends on what question we are asking. Perspective also shapes morality. One rule says telling the truth is always good. Another says protecting others from harm is good. In certain situations, these principles conflict. Both are ethically valid. Their clash creates a paradox of choice. We feel stuck not because one rule is wrong, but because real-world situations force us to choose between values that were never meant to be absolute in all contexts. Even time creates conflicting perspectives. Physicists know time is relative. Moving clocks run slower. From a stationary perspective, time flows one way. From a moving perspective, it flows differently. Both views follow the laws of physics. Reality allows both to be true at once. What feels like a paradox is a signal that our everyday intuition about time is incomplete. In everyday conversation, perspective clashes create smaller paradoxes. Look before you leap tells us to plan. He who hesitates is lost reminds us to act, tells us to act quickly. Both pieces of advice are wise. Each applies in different situations. The paradox is not in the sayings, it's in trying to apply one universal rule to all contexts. Wisdom lies in knowing which perspective fits the moment. Zooming in or out also flips truths. From far away, a coastline looks smooth. Up close, it is jagged and detailed. Both views are accurate, but they describe different scales. The coastline paradox shows how measured length increases the closer you look because smaller and smaller wiggles appear. Smooth and rough are both correct descriptions. The perspective defines the reality. In psychology, we see paradox in identity. A person might act differently with family, friends, or coworkers. Are they being fake or flexible? From one perspective, consistency equals authenticity. From another, adaptability equals authenticity. The paradox arises because self is both stable and evolving. Identity depends on context. Two valid views collide. Paradox also appears in power dynamics. Freedom and order both matter. Too much freedom creates chaos. Too much order suppresses individuality. Each value is valid. Their tension forms a paradox at the heart of society. Rather than picking one side, we balance them. The paradox is not a flaw, it is a feature of complex systems. Consider fairness in a courtroom. Treating everyone the same seems fair, but treating people based on their circumstances also seems fair. Equal treatment and equitable treatment are both compelling, yet they lead to different outcomes. The paradox reflects how fairness changes depending on whether we focus on process or result. Perspective can even reverse probability. Think of the birthday paradox. One view, 23 people compared to 365 days, seems small. Matching feels unlikely. Another view, 23 people generate 253 pairs, each capable of matching. Suddenly, it feels likely. The paradox arises from choosing individual-to-group perspective versus pair-to-pair perspective. Both are valid, but only one captures the structure of the problem. Quantum mechanics makes this even stranger. Light is a wave. Light is a particle. Both statements are true depending on how you measure it. The paradox is not in nature, but in our expectations. We want one identity. Reality supports multiple. Measurement perspective changes the observed behavior. The system does not break. Our classical logic does. Even language hides perspective paradoxes. Less is more seems self-contradictory, but in design, the idea is true. Removing clutter creates stronger impact. Simplicity can produce richness. From one view, less means subtracting. From another, less means focusing. The paradox shows how meaning shifts based on what we emphasize. Paradoxes also teach us humility. When two truths clash, our instinct is to pick a side. But deeper thinking asks why both seem reasonable. Often the answer is that each truth reflects a different frame. Problems arise when we try to force one frame to rule them all. The world is layered. One viewpoint seldom explains everything. Sometimes the clash happens across time. A choice that seems smart short-term may be harmful long-term. Saving money by cutting maintenance looks efficient today, but costly in the future. The paradox comes from choosing which time frame defines success. Both perspectives matter. Focusing only on one distorts judgment. Even personal growth contains paradox. To become better, we must accept ourselves. But if we accept ourselves, why change? Self-acceptance and self-improvement both matter. They seem to conflict until we realize they can work together. Accepting who you are now creates the stability needed to change. The paradox dissolves not by choosing a side, but by integrating the perspectives. Paradoxes are signals. They show us where our thinking is too narrow. They remind us that truth can stretch, bend, and overlap. A single viewpoint can be clear and still incomplete. When multiple valid perspectives collide, the paradox emerges, not to confuse us, but to reveal depth. The real challenge is not solving the paradox, but learning to hold more than one truth at the same time. At first, it sounds impossible. How can the future change the probability of the past? The past already happened. It's fixed. But probability isn't about reality. It's about what we know. When new information appears in the future, we update our belief about what most likely happened in the past. The event itself doesn't change. Our confidence about it does. This is the heart of Bayesian thinking. Imagine you take a test for a rare disease. Before the test, the probability you have the disease might only be 1%. After a positive result, that probability might jump to 50% or higher. The test did not change whether you had the disease yesterday. It changed your knowledge. You update your belief about a past fact based on a future result. That's Bayesian reasoning. New evidence reshapes old probabilities. Think about sports. A game ended last night, but you haven't seen the score. You believe there's a 60% chance your team won. Then you hear there was an insane comeback. That new clue makes a comeback more likely than a blowout. Your belief might jump to 80%. The game didn't change. Your information did. You just used the future, a result you learned later, to adjust the probability of a past event. Even simple coin flips show this. Suppose someone flips a coin out of sight. You don't know the result. To you, the probability of heads is 50%. Now imagine someone tells you, the coin landed on the table and rolled near the edge. Maybe you know from experience that coins that roll near the edge tend to land tails more often. At that moment, the probability of heads goes down, not because the coin changed, but because the new information influences your belief. The future information reaches back into your estimate of the past. This is normal in detective work. Investigators assign probabilities to suspects based on early facts. As new clues appear, they revise those probabilities. If an alibi is disproven later, the probability a suspect was guilty yesterday increases. The crime is over and done, but their belief about what already happened evolves. The future keeps reshaping the past, not physically, but logically. Let's explore a more structured example. Drawing cards. A deck is shuffled. The top card is dealt face down. You don't know what it is, but the probability it's an ace is 4 out of 52. Now, 5 more cards are dealt face up, and none of them are aces. Suddenly, the probability the face-down card is an ace jumps up. Did the card change? No, but your belief did. The future information, seeing later cards, changes the probability of the earlier card. This is exactly how Bayesian updating works. Even weather forecasts behave this way. Suppose a storm formed yesterday, but meteorologists didn't know the details. Today, new radar data arrives. That data changes the probability that the storm path yesterday moved north instead of south. The storm already traveled its path, but our belief about that path evolves as we learn more. The future provides clues about the past. One of the clearest examples is in medical diagnosis. A patient might have symptoms that don't appear until days after an infection. When the symptoms appear, doctors increase the probability the patient was already infected earlier. The body doesn't travel back in time, but the symptom, future information, reveals something about past reality. The probability that the infection happened before rises, even though the timeline stays the same. Bayesian thinking separates physical time from information time. Physical time moves forward. Information time moves whenever new knowledge arrives. Probability lives in information time. It shifts whenever new evidence appears, past, present, or future. Consider this scenario. You know someone has 2 children. Without more information, the probability that both are girls is 1/4. Now that person says, one of my children is a girl. Suddenly, the probability that both are girls increases to 1/3. The statement didn't change the children, but it changed your belief. One is a girl is information that alters probability about the past. This feels counterintuitive because we think probability should freeze once reality is set. But probability measures uncertainty, not reality. Poker players live in this world. A player makes a bet early in the hand. Later actions, bets, expressions, timing, provide clues about what cards they likely had before. The hand was already dealt, but the future behavior updates the probability of what cards were in play earlier. The best players constantly update beliefs about past events based on future signals. Even memory works this way. Suppose you vaguely recall leaving your keys on the counter. You're 70% sure. Later, you find your bag unusually heavy. Now, you update your belief. Maybe the keys are in the bag after all. The past action, where you put the keys, is already fixed, but the future observation, bag weight, changes your belief about the past. Your confidence updates to maybe 90% they are in the bag. You just used Bayesian thinking without realizing it. This kind of reasoning is incredibly powerful. It lets us use every clue, no matter when it arrives. It avoids throwing away evidence just because it came later. It turns uncertainty into a dynamic process. At every step, we blend prior belief with new data to get an updated probability. Then, the update becomes the new prior, ready for the next piece of information. Bayesian thinking also explains why witnesses can become more confident about what happened after reviewing surveillance footage or hearing others' stories. They are not changing the event. They are adjusting their belief about their own memory using new evidence. Sometimes this helps. Sometimes it introduces bias, but the mechanism is the same. Knowledge changes probability. Even when the past is 100% fixed, probability can logically fluctuate from 0 to 1 as we learn. If you don't know the result, the future is your ally in narrowing down possibilities. Every new fact cleans up uncertainty. Think about opening a sealed envelope. The letter inside was written long ago. Before you open it, probability reflects guesswork. After reading even the first line, you suddenly know who wrote it. Your belief about the past shifts. The content was fixed from the start. But probability followed your knowledge. This is why probability is not fate. It is not prediction only. It is a flexible measure of belief that moves with information. The future can't rewrite history, but it can rewrite our confidence about history. Bayesian thinking gives us the language to describe that shift. In the end, the idea that the future changes the probability of the past isn't magic, it's honesty. We don't live with perfect knowledge. We gather clues over time. Some clues arrive later, but still point backward. Probability isn't frozen in time. It updates with understanding. Reality happens once. Belief evolves forever. Infinity seems abstract, but it appears in many simple ideas. The moment we allow a process to repeat forever, strange things begin to happen. Logic bends, intuition fails, outcomes no longer match expectation. Paradoxes appear, not because infinity is broken, but because our minds are built for the finite. We understand beginnings and endings. Infinity erases both. It replaces clear boundaries with endless possibility. That makes even basic concepts slippery. Take Zeno's paradox. He argued motion is impossible because before you reach your destination, you must go halfway, then halfway again. Each step divides space into smaller pieces. The process never ends. If you must complete infinite steps to arrive, how do you ever get anywhere? The paradox feels powerful. Yet in real life, you take a step and arrive. How? Because infinite steps can happen in finite time when each step gets smaller. The math works, but our intuition cannot picture completing infinite tasks. We imagine endless time or distance. We cannot hold the idea of infinite division and finite completion in the same mental space. The Achilles and the tortoise version pushes this tension further. Achilles gives the tortoise a head start. Every time Achilles reaches where the tortoise was, the tortoise has moved ahead slightly. Achilles should never pass the tortoise, but of course he does. The paradox isn't about motion. It's about how infinity hides inside continuous motion. Our mistake is thinking of infinite steps as equal in size. Once we accept shrinking intervals, the impossibility vanishes. Still, the paradox lingers because infinity forces us to abandon simple counting. Hilbert's hotel adds another layer. Imagine a hotel with infinite rooms, all occupied. A new guest arrives, and the manager moves the person in room 1 to room 2, room 2 to room 3, and so on. Room 1 becomes free. The hotel was full, yet it made space. Even stranger, bring in infinite new guests, and the manager can still fit them by shifting everyone to even-numbered rooms. Now all odd-numbered rooms are free. Infinity breaks our idea of full and empty. Both can be true at once. The math is correct. Our intuition revolts. These paradoxes arise because infinity doesn't obey the rules of finite logic. In the finite world, adding people to a full hotel is impossible. In the infinite world, the structure of full is different. We cannot lean on everyday language. Infinity demands precision. Without it, we fall into contradiction. Consider geometric series. Add 1/2 plus 1/4 plus 1/8 plus 1/16 forever. Intuition tells us this sum should grow without bound, but it adds up to exactly 1. Infinity doesn't always lead to endless size. Sometimes infinity produces exact, finite results. Again, our finite minds feel the conflict. How can infinite parts create a finite whole? Yet we see it in reality. Stacking smaller and smaller actions can lead to a complete process. Infinity can compress. Even numbers themselves hold paradox. There are infinitely many whole numbers. There are also infinitely many even numbers. At first, it seems like the set of all numbers should be larger. But you can pair every whole number with an even number by doubling. The sets match in size. Two infinite sets can have the same length, even when one appears embedded inside the other. Infinity refuses to follow common sense. It forces us to accept that part can equal whole when the part is infinite. Probability gets twisted by infinity too. Imagine flipping a coin until it lands heads. Most people think there's a chance you never get heads. But mathematically, the probability of infinite tails is 0. Yet 0 probability does not mean impossible. It means so unlikely that it doesn't matter. The infinite process gives us a 0 probability event that still sits inside the realm of possible things. Infinity blurs the line between possible and probable. Now look at the St. Petersburg paradox. A game pays $2 if you get tails on the first flip, $4 if tails on the second, $8 if tails on the third, and so on. The expected value, the average payout over infinite plays, is infinite. Yet most people would not pay even $20 to play. Infinity makes the expectation explode even though the actual outcomes are usually small. The game rarely pays much, but the possibility of a huge payout exists. Infinity stretches expectation beyond human comfort. Our instincts about value cannot grasp infinite tails. In calculus, we accept that instantaneous speed exists. A car's speed at an exact moment is a real number. But how do we measure something over zero time? Speed is distance over time. If time is zero, the math breaks. The solution is to use limits, approaching zero without reaching it. This is another infinite process, slicing time into infinitely small intervals. We don't measure motion at a moment. We measure motion around a moment. Infinity hides again in how we define precision. Fractals deepen this strangeness. A coastline, when measured with a large stick, looks short. Use a smaller stick and the length increases. Use an even smaller stick and it increases again. In the limit of infinite resolution, the coastline can become infinitely long, even though it fits in finite space. Infinity lives in the details. The finite mind sees a shape. The infinite mind sees endless complexity in the edges. Infinity also complicates fairness. If you divide infinity in half, you still get infinity. You can remove infinitely many elements from an infinite set and leave an equally infinite set behind. Our sense of subtraction cannot handle this. We expect removal to reduce something. Infinity laughs at that expectation. In thought experiments, infinity often creates self-reference paradoxes. This statement will take infinite time to evaluate, or the set of all sets that do not contain themselves. These logical knots come from trying to apply finite logic to infinite self-reference. Our brains want clear boundaries. Infinity erases boundaries or loops them back on themselves. Even convergence and divergence can be counterintuitive. The harmonic series 1 plus 1/2 plus 1/3 plus 1/4 seems to shrink, but it diverges to infinity. Meanwhile, 1 plus 1/4 plus 1/9 plus 1/16 converges to a finite number, even though each term is small in both cases. Infinity magnifies subtle differences in structure. Two similar-looking infinite processes can have opposite results. Our pattern-seeking mind expects consistency. Infinity rewards nuance. Probabilities over infinite sequences reveal more paradox. Suppose you randomly choose a real number between 0 and 1. The probability of picking any specific number is 0, but you will pick some number. Infinity allows zero probability outcomes to be guaranteed. The event is certain and impossible at the same time, depending on how we define probability. Our finite minds want events with zero probability to never happen. Infinity disagrees. All these paradoxes come from the same source. Infinity breaks our mental tools. Our brains evolved to survive in a world of limited things. We deal with objects, time spans, distances, all finite. When a process has no end, or when a set has no limit, we lose our footing. Infinity is not just a large number. It's a different category of concept. It stretches logic to its edge. It forces us to confront that some truths can only be seen through abstraction, not through instinct. Infinity does not misbehave. It obeys precise rules. The paradox arises because we try to use finite patterns in infinite territory. When we adjust our perspective, the paradoxes dissolve, but the discomfort remains. Infinity is the mirror that shows the limits of how we think. Bot. A game can look fair on the surface while hiding mechanics that tilt the outcome. We often judge fairness by appearance. Equal choices, simple rules, balanced options. The probability reminds us that structure matters more than looks. Two players can face the same choices, but not the same chances. A game can follow the rules and still produce results that favor one side. Fairness in design is not the same as fairness in outcome. Consider Monty Hall. 3 doors, 1 prize. You choose a door. The host opens another door with no prize behind it and gives you the option to stay or switch. It looks like a 50-50 decision. 2 doors remain. That feels fair. But the structure of the game hides an imbalance. The host knows where the prize is and never opens that door. His action loads extra probability onto the door you didn't choose. Staying gives you a 1 in 3 chance. Switching gives you 2 in 3. A game looks symmetric but isn't. The mechanics make it unfair to stay, even though the surface looks neutral. The birthday paradox feels similar. You gather 23 people and ask if any 2 share a birthday. Most expect low probability because 23 out of 365 seems small. But the true comparison is not people to days, it's pairs of people to each other. There are 253 pairs in a group of 23. The number of comparisons scales quickly. A game of do any 2 match looks fair when thinking linearly, but becomes heavily biased toward matches because of combinations. The mechanics overpower intuition. Casinos exploit this gap between appearance and structure. Roulette wheels have equal sections of red and black, but then they add green zeros. Now red and black bets lose slightly more often than they win. To players, it still looks like a fair 50-50 gamble. The hidden greens take the edge. The game looks even but favors the house. The fairness is cosmetic. Slot machines do the same thing. Each reel spins freely, or so it seems. Behind the scenes, weightings are applied to certain symbols. Some symbols land more often than others. The machine offers huge jackpots, but with tiny probabilities. The randomness is controlled to match the casino's desired payout rate. Players see spinning reels and flashing lights. You don't see probability tables and payout structures. The surface feels fair. The mechanics dictate profit. Even everyday choices hide unfair structures. Imagine 2 job applicants. Both complete the same test. That feels fair. But one had years of preparation and resources, while the other had none. Equal rules do not equal equal opportunity. Systems often treat equality as fairness, but ignore the mechanics that influence outcomes before the game starts. Consider voting. 1 person, 1 vote seems fair. But district boundaries, voter access, and turnout rules can shape results more than the votes themselves. The mechanics can amplify or suppress certain voices. Without changing the rule, everyone gets 1 vote. The surface rule is fair. The structure behind it might not be. Even in sports, fairness can be hidden. A basketball court is the same for all players, but one team may have traveled across the country the night before, while the other slept at home. Same game, same rules, different conditions. Or consider baseball parks. Some are smaller. Some have unusual walls. A home run-friendly park benefits power hitters. The rules don't change, the environment does. The mechanics shift balance where the rulebook remains neutral. Probability often hides bias in design. If a game allows players to make choices but hides crucial information, it favors those with better strategies or insider knowledge. For example, in card games like poker, everyone receives cards at random. That seems fair. But experienced players know how to calculate odds, read behavior, and control pot size. The random cards are only part of the game. Information asymmetry drives success. The surface randomness hides a deeper skill gap. Marketing uses the idea of fairness to mask mechanics. Buy one, get one free sounds like a fair deal, but the original price may be inflated, or the second item may have little value. The deal feels fair because it follows a symmetric pattern. The structure exploits perception. Even in simple puzzles, fairness can be misleading. Imagine a game where you and I both flip a coin. If it lands heads twice in a row, I win. If it lands tails twice in a row, you win. This feels fair, But what about heads, then tails? Or tails, then heads? If the rules avoid defining those cases, the designer can assign outcomes that favor one side. A fair-looking rule can conceal an unfair mapping of results. One of the clearest examples of hidden mechanics is the Monty Hall variant, where the host doesn't always open a door. If the host sometimes opens and sometimes doesn't, the rules become ambiguous. Now, players can't rely on switching as the best move. The fairness collapses because the mechanics are unclear. Predictability is part of fairness. Uncertainty in rules is a quiet form of imbalance. Probability also reveals how timing creates unfairness. If one player acts second, they may gain an advantage by responding to the first player's move. Chess is balanced with alternating turns, but even so, the first move provides a slight edge. Many games compensate by offering mirrored setups or alternating advantages. Without these adjustments, symmetry in rules can still lead to asymmetric outcomes. Social systems hide unfair mechanics through presentation. For example, merit-based systems sound fair, but merit is often measured using criteria that favor one group more than another. The structure defines success in a way that appears neutral, but reflects hidden bias. The mechanics behind the metric determine who wins. Fair-seeming choices can also trap people. Consider a game where you can quit any time with your current winnings or continue for the chance to double everything. Each step feels fair, but the structure encourages people to take more risk than they should. The game leverages loss aversion and greed. The mechanics exploit psychology, not probability. Even statistics can hide unfairness. When we look at averages, we often assume they represent everyone equally. But averages can mask group differences. For example, a new policy might improve average income while making the poorest worse off. The overall result seems fair. The mechanics within the distribution tell another story. Probability teaches us that fairness is not about what's visible. It's about structure, information flow, and underlying rules. Games that hide mechanics can steer outcomes while pretending to offer equal chances. To see true fairness, we must look deeper than the surface. We must analyze how choices are created, how information is shared, and how the rules interact with human behavior. Only then can we see whether a game is genuinely fair or only wearing fairness like a costume.